Okay, good morning everyone to the second day of our machine learning classes workshop. We are very happy to announce Andrea Liu from the University of Pennsylvania to present her view on machine learning classes. She basically started all of this, so we're very happy to have you here, Andrea. Go ahead.
Thank you, Gerhard. That's very nice. It's really my students, Sam Schoenholz and Jos Trubuk, who deserve the credit for starting this. All right, so, well, I'm going to tell you about work, and I'm sorry, I can't even say it's on the archive yesterday because it is not on the archive yet. We hope it will be in the next month or two. All right, but it's recent work that we've been doing on plasticity, and I particularly want to highlight three people, my former postdoc, Ge Zhang, who's now tenure track at the City University of Hong Kong, and Tao Yang, who is a student with Rob Riggleman, and Hongyi Shao, who is a postdoc with Doug Durian. He's now in Germany, and he will soon be starting a tenure track position at the University of Michigan. And Robert Ivensey, who formerly worked with Rob Riggleman and also me, and is now at NIST. All right, so so here is the problem, right? When you take a system and you shear it infinitely slowly at 0 temperature, or very slowly at 0 temperature, right? These are configurations that were attained by Misaku Ozawa and Ludovic, and using Monte Carlo swap. And so these are configurations that were quenched from different temperatures. So this is a system that was quenched from a high temperature, and this is a system that was quenched from a very low temperature, down to 0, okay? And when you take these two systems, and now you shear it very slowly, okay, 0 temperature, what you see is a stress-strain curve that looks like this. So it's initially elastic, right? But then you start seeing these stress drops, these little stress drops. As the system goes, it eventually flattens out. And I keep pushing, I still don't, for some reason, have this plot of this flattening out eventually, okay? And this is, for the brittle case, though, you see something very different. It starts out elastically, but then you see this very large stress drop, and that signals the formation of this shear band, okay? So that's brittle behavior. And what we would like to understand is, first I'm going to talk about different ways of adjusting this ductility, but we would like to understand, what are the microscopic factors, the microscopic physics that controls ductile versus brittle behavior. So this is one way of controlling ductility, is by how equilibrated the system is before you quench it. And the more equilibrated it is, the more brittle it is. Here's a different way of controlling the ductility, is through the interaction potential. So it turns out that systems with a shorter attractive range are less ductile. So here is the original Leonard-Jones, and as you shorten the interaction range, what you see is that the system becomes more brittle. And here's an example. I wouldn't say it's more brittle, I would just say it's maybe less ductile is the way to put it. So here's the system, the original Leonard-Jones system, and here's the system with the shorter range. And you see that the strain is more localized, okay? At the onset of, when you start straining the system, the strain is more localized. So these are systems that are being pulled. Okay, these are polymer pillars that are being pulled. Okay, and so you do see strain getting localized in this region where it's necking down no matter what, but what you see is that it gets more and more localized as you make the interaction shorter in range. And you see a similar thing in these granular systems. So I should have said this was work done by my colleague Rob Riggleman at Penn. This is work done by Doug Durian. So these are grains that are suspended at the interface of oil and air. So there's a capillary attraction that pulls them together, okay? And then, of course, a hard range repulsion. So this capillary length is just set by the surface tension, density, and gravity. Okay, so that's fixed. But what they vary here to vary the attractive range is they vary the size of the particles. So there are two sizes of particles, 1 millimeter and 3 millimeter. What you can see is in the 1 millimeter case, you see typical ductile behavior. In the 3 millimeter case, each one has a small stress drop. Okay, not very big. I wouldn't say it's brittle, but it is. And the strain is more localized. Do I have pictures? So there you see it's a pillar that's being pulled apart, and it's held together. The grains have this attractive interaction. You can see that they are attracted to each other. Okay. Oh yeah, and here again in the 1 millimeter case, you see that when you do this, the initial thing as you start pulling them apart, when you're seeing this sort of behavior up here. In the smaller system, the strain is not so localized, it's spread throughout, and in the larger system, it's much more strongly localized into a region, okay? So that's what's changing. Oh yes, and then again, you see it in this system. Sorry, this is the polymer, this got out of order. This is the polymer nanopillars. Again, they're all ductile, but what you see is that again here the strain is getting more localized. Okay, in the pillar that is more deeply quenched. Okay, so if you look at the dynamics during stress drops, no matter whether it is the small stress drops that you see in the ductile systems or the very large stress drop that you saw in the very brittle system, and again, this is, I should say this is Misaki's data. So if you look at the dynamics during the stress drop, okay, this is the ductile case, you see localized rearrangements. I hope you can see them. Very localized rearrangements that fluctuate around. Another one can appear at a rather distant location, and so forth. So you have these isolated, localized events that can be well separated in space. If you do the same thing for the brittle system, and this is the very large stress drop, okay, and the very brittle system, you see the same thing. Okay, that's on the right. Okay, you see very isolated rearrangements that fluctuate around and can jump. But what you see is that they are always concentrated in that region that eventually becomes a shear band. Okay? So there's something very similar here in that the avalanches, no matter what, are composed of these localized events that can trigger other ones far away. Yes?
Can I just ask you a question about the picture on the left? To me, I see a grid underneath this. Do you know what the origin of the grid is? I see squares everywhere. Like white, an underlying white lattice almost above squares.
Yeah, that's true. I hadn't noticed that before. Do you see it on your screen as well? I do see it on my screen as well. I hadn't really noticed that before. Okay, that's interesting. This is not many copies. This is really a large system. It's not many copies of a small system.
No, I get that.
I think it's enough.
I'm not.
Just
That's a
I think
yeah.
it's a PNG.
You think it's a PNG error? Okay. Okay. It's funny it's not on the left, but okay. So so how are we going to do this? We use softness. So the idea of softness, right, is that you. Sorry. Okay, so let me try to. It's early in the morning, and I have to say, I'm incredibly distracted today because of politics in the US, and so I'm finding it almost impossible to think about plasticity. Okay, all right, so machine learning. Let me get my brain in gear. We have softness. We have this quantity softness, which for this talk we just used the local pair correlation function, the radial one. In continuum language, right, it's a weighted integral of the local pair correlation function for each particle. You know, we do a discrete version of this, of course, where we bin in radius. And we use a support vector machine in some of this, so I will talk a little bit more about that. But this is basically the approach that we will use, is that we come up with some quantity that we feel is where the weights here are chosen to correlate with rearrangements, strongly with rearrangements, okay? And what we do when we train, we're training on the state just before the stress drop. So here we have many, many stress drops. Here we only have the one, but we have many, many configurations that we trained on, okay? So we're training on basically the mode that goes to 0. There's a vibrational mode that vanishes right at the onset of the instability, and we are training on that mode, okay? You know, we started out training on the non-affine displacement of each particle. So we fit the neighborhood of each particle to the best strain tensor, look at the squared deviation from that, okay, per neighbor particle. And but this turns out, if you look at the mode that goes unstable right at the stress drop, you see that there's particle or some particles rearranging here, but there's this very large corona of large values of the non-affine displacement that emanates from this, and that's expected because this is an elastic system, right? So so you don't want to just concentrate on this. So to get rid of the power law tails here, what we do is we look at this quantity, we call it delta squared min, which is basically just d squared min, this non-affine displacement for my particle I, divided by the average over its neighbors. This eliminates the elastic tail, and if you look at delta squared min, it looks like this. Okay, so it's now homogeneous across the whole system. And so the nice thing about this is that we can, if we were to just use d squared min, our training set would just be the rearranging particle here and maybe some particle way out here, okay, for our training set with a very small non-affine displacement. And that would be very wasteful of data. We don't have that many configurations from Misaki and Ludovic to be able to just use 2 particles for every configuration. So we train instead on local minima and maxima of delta squared min. So there you can see then there are many of them. Okay. But the problem is that softness, it turns out, is an extremely poor predictor of rearrangements in brittle system, or a rather poor predictor that was shown in this paper that David mentioned yesterday that he was he pulled together as an amazing feat, where compared many different predictors of rearrangements, and so what we do instead is we trained, instead of training on delta squared min, what we ended up training on was the local yield stress. The local yield stress does turn out to be an excellent predictor. There's David. Yeah, your heroic effort in pulling this paper together was quite impressive. So the local yield stress is quite a good predictor of rearrangements. And so what we wanted to do, instead of calculating the local yield stress, which is extremely expensive, we wanted to train for a structural predictor of the yield stress instead. And so what it turned out that the support vector machine is a very poor predictor, probably because it is a scalar, right? And the local yield stress, there is a direction associated. You shear in all directions. This is what David talked about yesterday. So the idea is you take a little region, you shear in all directions, and you say, what is the direction in which the yield stress is the lowest? And that's the local yield stress. Because there's a direction associated, probably, we think, the support vector machine or support vector regression work quite poorly. And what we end up using is a neural network. This is ResNet. Okay, it's an ugly thing. I'm not defending it in any way except to say that it works quite well. Okay, and we were in a hurry. Okay, so yes.
The input to the deep net is always the GOR.
The input into the so it is delta squared min. Yeah. We just feed it images of the particle and its little local neighborhood. Okay. So we just feed it these images. The particle is always at the center, and its neighborhood.
At a certain scale. So the neighborhood is up to a certain
up to just about two. It's about 5 particles across. Okay, and then yes.
You actually pixelated the image, so the n by n image somehow smeared the particles, or how do you take the particles into account?
Yes, so it's just a picture of the packing. Okay. Yes, that's all it is, and it's pixelated. That's correct. So this is the ugliest, stupidest thing you could do. We just feed it these images, okay, and then we train it on delta squared min of the particle. Okay, all right. So and you see what comes out. So this is the probability of rearranging. This is on a log scale, so you see it covers several orders of magnitude. Okay, so it's a strong function. It's a reasonably strong function of softness. It's not terrible. Okay, but it's actually, it turns out that predicting local yield stress, a structural predictor of local yield stress, is a better predictor of rearrangements. This is rearrangements than to train on rearrangements themselves using a support vector machine. So what you see is that over the percentile range of the structural predictor of yield stress, which I will not commit the crime of calling it yieldness, but it is, we just call it Y. Okay, so this is our structure predictor. Over this rather small percentile range of it, you see the probability of rearranging changing by many orders of magnitude. So it's quite sensitive. All right, so now we have this quantity. What do we do with it? So what comes out of ResNet is a quantity that's between 0 and 1. So what do we do with this? So I should say that it was only for the most brittle system, for Ludovic's system, that we used Y, the local structure predictor of yield stress. For the other two systems, we did use softness trained with support vector regression. And it turned out on delta squared min. Okay, and that turned out to work quite well for those systems. And I should say in those systems, and also in this, we use a single training. So for the neural network, we train on the brittle system, and we can apply it to the ductile system, or we can train on the ductile system, we can apply to the brittle system, it's fine, okay? For the others as well. Okay, so it's a single training for both of the systems that we're going to be comparing. So for the granular system with 2 different diameters of particles, okay, it's a single hyperplane for both of them. Okay, all right, so now in order to build a model of plasticity, so the idea is we're going to use these machine learned quantities, and then we're going to build a model of plasticity. So the idea is the following. We look at how a rearrangement changes the softness, or Y. Okay, it could be softness, it could be Y. It doesn't matter. So, so it changes directly the softness nearby, right? Because you're scrambling the local neighborhood of the particle. So when you scramble the local neighborhood, you change the softness of all the particles that are involved, okay? So there's this direct effect on the softness nearby. There's also a far field effect, so that's a near field effect. There's a far field effect coming from, it turns out, the volumetric strain, which changes the softness far away, okay? And then the rearrangement also gives rise to a deviatoric strain, and that combined with the softness, okay, which determines the yield stress, okay, can push you over the edge to have another rearrangement. So that's the model. Yeah.
Why the deviatoric strain doesn't change the softness? Why only the
That turns out to be a much smaller effect.
I see.
Yeah, and I'll just show you. So here's how we do it. What I'm laying out is a framework that we then just use for each system. Okay, so what you do, and these particular plots are taken for a system of Hertzian jammed particles. Okay, under athermal quasi-static shear. All right. So what we do is we look at the strain as a distance from the rearrangement. So we take many rearrangements. This is an ensemble average, okay? And you look at the strain away from the rearrangement. You look at the R dependence, the radial dependence, okay? Both of the strain itself and the magnitude of the strain, and you look at the angular dependence, okay? And what you see is the volumetric strain has a piece that decays like 1 over r squared. This is in 2 dimensions, okay? And it has this form, this dipolar form, stress dipolar form. Stress, okay, sorry. Electric dipolar stress, a quadrupolar. Okay, anyway. I'm sorry, I can't even focus today. All right, so it has this form. The deviatoric strain, okay, is 1 over r squared as well. It is isotropic, right, because this is just the deviatoric component of the strain. We're average. All the angles are averaged over, it has to be. And then there's shear strain in the xy direction, 1 over r squared, which has this characteristic quadrupolar form. All right, so, so by looking at this, then we can look at the change of softness, okay? So here's the change of softness as a function of distance. What you see in the far field is that it follows the volumetric strain. Okay, it looks exactly like the volumetric strain. Okay, and in fact, it has this 1 over r squared tail. And if you look at the angular dependence, it looks like this, where blue is less soft, red is softer. And indeed, if you look at the volumetric strain, that's where the system is, it's locally dilated, and here's where it's locally compressed. Okay, so, and that makes perfect sense. Changing the density makes a big difference to softness. Okay, so. But it doesn't work very well. So far away, then there's this term, which is just proportional to the volumetric strain. And we see this in all 3 of the systems or all 6 of the systems, I should say, that we look at, okay, that we're looking at. It's always the volumetric strain. All right. The near field term is more complicated, okay? So what you see is that in the near field, okay, the change of softness does not agree with the volumetric strain at all. But if you subtract off the volumetric strain piece, it turns out that it's quite simple. There's a piece that decays with distance from the rearrangement, okay? And then there's this piece which wants to restore softness to the average of the neighbors, okay? So this is the effect nearby. All right. So let me just first say a word about ordinary elastoplasticity models. What you do is you have a system of blocks, okay? And on each block, you put a local strain, epsilon xy, and a local yield strain, okay? And then you apply the strain. You just add some increment to the strain on each block, xy strain on each block. And then when the strain on a given block reaches the yield stress, okay, the yield strain, then you reset the strain to 0 for that block. You say there's been a rearrangement, you record that, and you update the strain on the other blocks according to that elastic kernel, the strain that exerts on all the others, okay? And in most models, right, the local strain distribution is fixed. It never changes, and it's imposed by hand. Now, it's usually a delta function, but you can do something more fancy. And what was shown recently in this work from Mathieu Viart's group is that if you just change the magnitude of that yield stress that you put in by hand, that yield stress distribution, right, you can get brittle or ductile or brittle behavior, depending on the magnitude of that yield stress. That the bigger this yield strain is, if you push it out to this dark curve, it has the highest yield strain, then you see brittle behavior. I can barely even talk. I'm so sorry. I'm very, very upset about probably what's going to happen. Okay, so today, well, not even today. Okay, so all right. So what we do is we develop a lattice model that's similar to the elastoplastic model, okay, except that it contains structure. So we call it the structural elastoplastic model, which is a mouthful, so we call it the STEP model for short, okay. And this includes that interplay that I was just describing. We put, in this case, we put two components of strain. We need the, this is a spell check thing. Local deviatoric strain is a tensor, okay? It's got components epsilon xy, xx minus yy. So we keep each component. We keep the softness on each block, okay? So each block has a softness, and each block has a yield strain percentile. What do I mean by that? It turns out that if you look at the softness of each, look at particles of a given softness, okay? And there's a yield strain distribution corresponding to it. Okay, so particles of the highest softness, okay, have a yield strain distribution, which has a lot of contributions at the low end, okay, and a small median. Okay, this is the Weibull. These are fits the Weibull distribution, which is an extreme value distribution, which is expected because the local yield strain is this. You take always the direction in which the strain is the yield strain is the lowest, okay? So, whereas particles with a very low softness, which are much less likely to arrange, have a yield strain distribution that's quite different, okay? So, so basically, for each block, we assign a yield strain percentile. So which percentile in this distribution is random, okay? But the softness determines the distribution. All right? And then we apply strain by incrementing the xy strain, as usual. The local yield strain is not an explicit variable, right? It's softness, or the structural proxy for the yield stress here that we use. All right. So, so now what do we do? We're going to just set the block size to the particle diameter, okay? But we have seen that when we look at delta squared min, and I should say it's delta squared n, not d squared min, there's a correlation length. If we look at correlations of delta squared min, and you saw it, they were correlated in space, okay? So, and that takes into account that a rearrangement does not involve just one particle, okay? So we allow, when this rearranges, neighbor blocks can also rearrange, but with this length scale. That's the size of the rearrangement. And this is because, unlike elastoplastic models, which fix the block size to be the total size of the rearrangement, so it can be many, many particles, okay, we're fixing the block size just to be one particle. So we take care of the size of the rearrangement that way, okay? At the rearranging sites, we release all the strain, which every time you have a rearrangement, you change your yield strain percentile, and then you just let the softness evolve according to this thing that we came up with, okay? And this just shows you that it works quite well. These are the Monte Carlo swap systems. So here's the more ductile one. This is the actual this is our model, okay? The step model, these are the actual simulations. Here's for the brittle one, there's the simulation, here's our model. And so you see qualitatively, it is showing the right thing, okay? And I should say that when we do this interplay, we work this out for all 6 systems. In other words, for these 2 systems, okay, we have worked out that interplay separately. But what we find is that, in fact, for these 2 systems, everything is the same, okay? All of these, the decay, you know, all of these, the proportionality factor for the volumetric strain, you know, all of these things, the proportionality for the applied strain, how these change softness is identical, okay, for the 2 systems. So that's good. That emerges. We're not putting that in by hand. Let's see. Here are the polymer pillar simulations. Here are the simulations. Here's the step model. Here are the simulations showing much more strain localization. This is as a function of strain, okay? You see it developing and concentrating in this plane, and it's done. Am I done? I'm out of 5 minutes. Okay. Here are the granular experiments. Again, you see as a function of strain what happens in the ductile system, in the step model, in the experiments, and in the step model and in the experiments. Okay? So qualitatively, quite good. Quantitatively, not bad either. So the particle simulations here are light blue. Okay, this is Monte Carlo swap. The step model predictions are dark blue. Okay, light red and dark red. Okay, so not terrible. The granular rafts are actually quite a bit better. The polymer nanopillars, okay, not terrible. Capturing things qualitatively for both the stress-strain relation and the softness versus strain, the average softness versus strain. Okay, fine. So what's the big deal? So the only things that can change when we're comparing the 2 for each system, right? We have each system, we have 2 realizations, one which is more ductile and one which is less ductile, okay? The only thing that can change in these are the softness distribution, okay, the size of the rearrangements, and these, the range of the rearrangements and these coefficients here. All right? So how can we look at this? So what we do is we take the brittle system, okay, the more brittle system in each case, and we take our step model results for that, and then we vary each of these things continuously between what we get for the ductile system, brittle system, towards what we get for the more ductile system. Okay, so all of these things, we just vary them continuously one by one, and we see what does it take then to see a stress-strain relation that corresponds to the more ductile case. Okay, and in the case of soft disks, I told you nothing else changed except for one thing, and that was the distribution of Y, okay, which was very different in the 2 cases. So it's simply the initial distribution of the yield stress, okay, which changed this behavior, okay? And that's, of course, exactly what it should be, because what changed in that system was the preparation history. Everything else was the same, okay? So this indeed gave us the result, a reasonable result, okay, that it's just the distribution, the initial distribution of the structural proxy for yield stress that made the difference. So now let's look at the granular system. In the granular system, you see that there are two things that each could make the difference, okay? And so we can't really distinguish between them, all right? But one of them is that the yield strain in the more ductile case has a weaker dependence on the softness, okay? And the second thing is that in the case of the more ductile case, well, in both cases, what we find is that this decay of the short-ranged effect, how does the short-range softness change when you have a rearrangement, decays with the distance divided by the interaction range. And that is what's changing in the two systems. And so in the more ductile, the short-range facilitation effect is shorter range. Okay, the near field effect is shorter range. All right, so just to say that when we translate into this lattice step model, what it does is it gives us this insight into what is affecting ductility. Is it the size of the rearrangements? Is it the range of the short range facilitation? Is it the long range piece? We can take it apart and really understand that physics, okay, using these models. And so that's the story. Just these are the people who did it. Thank you.
Thank you very much, Andrea, for this great talk. We can't wait to see it on archive. All right, so are there any questions?
Hi, Andrea. Just to make sure I understood, in the lattice model, you are just keeping track of the softness, or also these volumetric changes and so on?
No, we don't keep track of the volumetric changes, just the softness. So we just update the softness.
Okay.
So we keep track of the softness and the local deviatoric strain and the yield strain percentile.
And the way one softness affects another is because of these other reasons, but you don't keep track of these fields.
We don't keep track of those.
Okay, thank you.
Exactly.
Hi, Andrea. Thanks for the great talk. I thought it was very inspiring to see the machine learning turn into an actual physical model, which is great. But now I'm wondering, it's all based on the softness thing, which, as I understand it, is still this support vector thing, right, where you have a weighted integral of your G of R's. Is there any physical interpretation that you can give this softness in some way? Is there some way I can understand, like, if I have a certain arrangement of my particles that gives me a lower softness? Is there some intuitive picture that you could give me?
Yeah. What we have found is that softness is, the weights are highest for the peaks and valleys of G of R. And for the first peak and then the first valley, okay, they're the strongest. And in fact, you can capture most of the prediction accuracy of softness simply from the height of the first peak and the first valley. Okay, that actually captures what, something like 82%, okay, of the rearrangements. So it's actually quite good. And so what we view it as, and so softer particles have lower peaks and higher valleys. So we view softness as simply a quantification of the cage. It's just telling you how strong it is. Yeah.
So Andrea, maybe I missed it, but in your new step model, do you still use the long-range elastic interactions as in the previous versions, like the Eshelby kernel?
Yes,
and, yes. So these are still present. Is that correct?
Correct. It's that Eshelby kernel, but it's not exactly the Eshelby kernel. So what we found was that, in fact, it was the deviatoric stress that was so important. So instead of doing this, we actually propagate that.
You only do the middle row, is that right?
Well, we update epsilon. This is just the magnitude of it. It's so So we do have epsilon xy, but we also have epsilon xx minus epsilon yy.
Okay, okay.
Okay,
So,
because that's what's important.
I guess what I'm wondering is your block size is now the size of the particle. And in principle, these are far fields that you're looking at there. So isn't there a contradiction? Shouldn't there be a length scale at which these far field elasticity solutions break down and you start to see sort of discreteness of the material? You know what I'm asking?
Yeah, so so that's right. This is the price we pay for having this near field softness effect that we want to include, right? So because we want to include the near field effect on softness, the direct effect, that's going to, we include this far field term at all distances. Okay, so we don't just keep this in the far field. This contributes even close by. It's not a big effect. This is bigger, so this dominates.
So you think
But
that
so it doesn't make that much difference.
okay. So you think that's okay?
Yeah.
One last question.
So I was wondering, compared to the elastoplastic model, so clearly you have put a lot of more, let's say, physics and refinement. But so, for example, for the property of the yielding transition, or for things like, I mean, there are some exponents that people have tried to compute. What do you think? Other things really, I mean, there are clearly quantitative things that one gets with this model, one cannot get with the elastoplastic model. But are there things that are, I don't know, that are really crucial? Otherwise, qualitatively, it's going to be completely wrong. So, for example, yeah, I don't know. I mean, we try to compute the property of the critical point associated to the Brichter to ductile transition. One could wonder whether one needs to go to more richer model, or there are some things on the description that you gave that are important for the quantitative description, but maybe not for the qualitative. I don't know if you have, I mean, comments on this.
Yeah, so that I don't know. This is something that we want to do, is to look at that, look at the transition brittle to ductile, in using Misaki's data, but we haven't done that yet. Yeah, so I don't know how much it's going to affect that. But the point is that here it is all emerging. We're not putting in anything about the yield stress, right? It is emerging from the structure. So that's a main difference. It's more a conceptual thing. So it can capture these things the other models can't possibly look at. How does the structure evolve, for example, as this happens? Whereas we can look at what's happening to the average softness during this process. That was one of these plots, right? This is how the average softness is evolving as you're straining the system. That's not something that the other models could possibly look at. So, yeah.
Sorry, and in these cases, so when along the curve, so you have trained the system at the big,
We trained the system there.
Sorry, the K that you use, I mean, all the properties that you use are recomputed at each epsilon?
Oh,
or
no.
You just do once and for all, and then you use the model.
Yeah. The model is just the model. Whenever there's a rearrangement, this is what happens.
Yeah, so this property doesn't change during the...
None of these things change. They're just fixed through the whole simulation. Yeah, that's right.
Okay, let us thank Andrea again.
And let's thank Camille for the use of her
And
laptop.
then we will try to set up the Zoom. So under the YouTube link, everybody who follows online, you find the Zoom link where Victor will give his presentation.
Hi, Victor. We have to set up the...
Let me just grab my... Yeah.
Always
Chipping on this thing. All right. Thank you. Oh, the microphone. Forgot about that. Thank you.
So the next speaker will be Victor Bapst, who is working at DeepMind, and he has developed the GNN, which was already mentioned several times before in the workshop. So we are very happy to have him here as a speaker. And yeah, Victor, please go ahead.
And on predicting the dynamics of plastic systems with graph neural networks. So this is a quick summary of the work. What we did in this work is predict the propensity of particles in a Fibonacci mixture with graph networks. So we had about 4,000 particles in 3D, and we predicted the system at different temperatures, and for each temperature, for each equilibrated configuration, we additionally ran 30 dynamic simulation from there to compute the mean displacement of the propensity, and we predicted that with the network. And we went at temperatures close to the mode coupling temperature of the system. And what we showed in this work is that the approach offered from the existing methods at the time over a wide range of conditions. And we also try to do some work on analyzing the working of the networks and extracting knowledge from it. So I'm going to go quickly about the graph network architecture, because I saw the tutorial yesterday, which I can give a description of them. But so roughly, it looks like the picture on the top. So when you go from a 3D input, make a graph of it from it based on local structure. So you know, which particles are near each other. Then you pass that through a graph network, which I'm going to describe slightly more after. And from there, you get these propensity predictions. And graph creations so that are fairly easy. You just connect things which are, as I said, nearby, so less than 2 sigma. You keep on the nodes you have particle types information, and on the edges you have geometrical information, so relative distances between particles. And the way the network works is by aggregating information. So first you update edges, the connection between nodes, based on the state of the nodes it's connecting, and then you update the nodes based on the edges that are incoming into it. And when you do that many times, you can see that the information propagates through the graph, and so you can extend. So the radius of nodes that ensure the prediction for a given node increases as you apply the network more and more. And I think in this work we were using the same layer or a separate type, but you don't need to do that. You can use a different layer for every time. So in terms of related work, for that. Yeah, I think this is a bit more like what the state was when we published this. So most of the applications were based on softness, so the work that Andrea just presented, in the earlier work version of that. And this was a machine learned correlator based on 2 and 2 functions, and had been influential work that kind of started the application of ML to Lattice systems in this area before. And this could traditionally be compared to traditional approaches, non-machine learning based approaches for providing predictors of dynamics, and there are many of them, potential energy, soft modes, d by water factor, and so on. And an interesting point to make is that of course you probably would expect machine learning to do better than those at some stage, just because it's far more powerful. But then there's a question about what you gain from it. So of course, writing down an explicit descriptor and showing that it correlates with the dynamics is giving you more information as a researcher potentially than just fitting a black box to it. So this is a bit more recent slide, and I'm sure I'm still missing things in there. But this is more focusing on the ML work, and the things at the top are the things that were that existed. When we published the work, so the SVM work I already mentioned, which is using handcrafted inputs, local descriptors for each particle, and fits linear to them. And around the same time as our work, there was a conversion network applied to this problem as well, which is which is a standard approach and didn't work as well as the predictions we could do with the graph network, which is expected. And then the things at the bottom of the tables are all things that appeared later on. And so one thing was another version of convolutional network, but which was not trying to predict the full box at the time, but was centering, making a prediction for each particle based on its neighborhood. So it's a more expensive approach because you're making one box per particle, which you recenter. But in this work they showed that it was working well. In some setup better than the work we had. And then interestingly, there was a family of work that was trying to, and so this one, this convolutional network one found in mine in 2020 is even more expensive than ours. But interestingly, there were approaches later on that were going the opposite direction, trying to reduce the complexity and the number of parameters. So there's yesterday you heard about the idea of reducing the graph network to a set of features that can then be fed into a linear regressor. That's a work from Bottini and others in 2021. And I think you'll hear this afternoon about using an MLP to make this prediction again from local discrete loss particles. And these are this later model can get better performance than our network, I think. So yeah, I think there are kind of different trends in there. And finally, there's also this new version of the graph network that seems to do better and has this, it's very close to ours, I think, but it probably has a better loss and a better way of being trained and get similar performance to the MLP just about. And I think there are, to me, the interesting, like one thing I would say to open maybe the discussion a little bit on this slide is, I think if you take the graph network and you give it physical features, personally, I would be surprised if it did much better. So I don't think it's about necessarily the features per se, and I don't think that the fact that the graph network uses so many parameters is necessarily the issue. But what I find really interesting with like using simpler methods is to understand what you can learn from what and what's relevant for the computation. So yeah, I think it's really about which do you use and how do you use them to make it work. So coming to the results of what we did, again, I'm going to go pretty quickly over this. We had 400 examples for each training point, for each temperature, for instance, and we trained to convergence, and we report the correlation between the ground truth and the predicted propensities, and we compared to two machine learning baselines, including the support vector machine I mentioned earlier, and 3 instance-type baselines. And what we saw is that at the time the network was the one performing the best. So this is reporting the correlation as a function of the time for a fixed temperature, the lowest temperature. The vertical line is the alpha, and you can see that the method is proposed here. The blue one is about all the others in terms of the correlation. It does as you'd expect for a very short time, it does reach perfect correlation, then it decreases and it increases again, interestingly, as you increase the time. The physics-based methods are the three at the bottom, and technique at a shorter time scale. So the performance is optimum for a short time scale. And so this is another version of this plot where now we fix the time and vary the temperature. And this again shows that the method can work across a range of temperatures. So these are all temperatures above the most working temperature. So the point on the right here corresponds to the previous plot. And again, there is similar ordering of methods and similar improvements on using a more complex network. And these were pictures that we had from comparing the ground truth to our system for different systems and different models of different systems. And yeah, I mean, this is just, I think it's hard to make something precise out of it. I mean, in some cases the agreement is at an eye level is really good. I think if you look at the one on the left and then some others, their scale is up, but I think from this you can see that at least the model seems to be identifying regions where the dynamics happen. And I think so this was showing comparison between the model, so the ground truth at the top, the model in the middle, and then the soft modes, which is this baseline at the bottom. The soft mode doesn't have a time scale, of course. So it always makes the same prediction, which is why you would expect that it only does well at a particular time. And this is showing at which time this is occurring. So this is corresponding to the second or the second column, the first or second column actually. We looked at temperature generalization. So can we train a model at a given temperature, and how does it degrade when you go to other temperatures? And I think we found the behavior that you expect, that you have a kind of nice degradation as you change the temperature. So you do well on temperatures near yours, and then you degrade. What was interesting is that the network that we trained at a slightly higher temperature, so 0.47, could extrapolate very well to like lower temperatures. And that's of course interesting from a practical perspective, because you need more data. Like evaluating the network is typically much cheaper than training it. Like you need far less data. So if you can train models in cheaper conditions and that they extrapolate to like the harder ones, the ones harder to simulate, that could be quite interesting in practical. These were results on shared systems. So now we looked at the non-thermal systems and doing plastic deformations on the system, and again comparing the model to either other machine approaches or physics-based approaches, and again seeing a good correlation as you increase the tilt and especially at intermediate shear deformations. Now I want to talk a bit about what we did in terms of analyzing the results. So we wanted to go beyond just positive evaluation of the predictions, and wanted to understand whether we could learn something from what our network is doing. And there are some ways in which you can do that. You could try to kind of train minimal models on the data to understand what the baseline performance is on the input data. I mean, that's something that that we did one has to do is like, make sure try to quantify how far the parameter, how good can CFM method do. Another approach is to train models with like simplified input to identify which feature contribute to the prediction. So that's an analysis we do the work is like try to pin down what are the features that the network is using, and can you remove information from the network and see when it breaks. You can train variations of the model architecture, modify parameters, and what I'm going to describe here is about taking a pre-trained model, so not retraining it and modifying its input and seeing how it reacts to it. So the first thing we did is change the boundary condition. So when you make the prediction for a given node, you typically see the neighborhood at a large distance. And this is because the network is applied, I think, in case was 5 times, so that means you see at distance 5 for a given particle. But now you can try to kind of pretend that the neighborhood at a given distance is not there. So you change the boundary condition, you reduce it, and you look whether the prediction changes. And if the network is extremely low cost, if it only looked at the neighbors of a given particle, then that wouldn't change things as long as you keep the immediate neighbors. But if the network is using information from very far away, then that will modify the prediction. And what we were saying is that so for the shorter timescales, which are the green curves here, you can move things up to the nearest neighbor. You can keep only one neighbor in shell, and you still get a good prediction, which is restricted. And what was interesting is that when you look at larger timescales, the network is actually using these shells further away. So if you remove the first or the second shell, you completely degrade performance. And you recover performance only when you start to include up to 3 shells in a given node. And on the bottom right curve, I think we also were looking at the fact that this is the fact that the 3 colors are 3 different timescales. So green is the shortest one, and the blue one is the longest one, and the orange one is to alpha, and this is the one we need for the most context. And the other one we did is like slightly more gentle version of the previous, where you don't remove nodes completely, but you just change the distance a bit. So you take the shell at a given distance, and then you're going to push all the edges, on the distance on the edges by a some factor. So you're kind of pretending that everything is a bit further away at a given distance. And again, you look at how much it changes the predictions. So we're looking here at, so this is an infinitesimal change now, so we can look at the derivative of the prediction with respect to this change in distance. And what we saw is this interesting behavior where if you look at the 2 plots at the bottom, which are the lowest temperatures, then you have this thing where the effect is the most pronounced at a given distance. So if you look at how much is the prediction modified as a function of where you do the modification, so the x-axis here is between which shells are you increasing these distances. So if you're on the leftmost plot, this means you're just increasing the distance to your immediate nearest neighbor, and then as you go to the right, this means you're increasing the distance between the third and fourth or other neighbors. And of course, there are more of these neighbors, so there's a bit of competition between the numbers and the distance. And what this was showing is that the effect is the most pronounced around the third or fourth shells. And this was a good indication that the network was using this was propagating this information from further away in the graph. And yeah, I wanted to, maybe I was too quick. I wanted to give a quick presentation, but maybe I've been a bit quick. But I wanted to also open for future directions and open questions, and some of these things have been done already. So I guess one immediate question that maybe from more ML way of thinking is, do we do better with better networks? Because how much can we push these results? What's the limit to the prediction of the network? So there are some natural ideas that should help. For instance, our network was not invariant under rotations of the system. It's something that you want to have, at least locally. That should help in practice. It doesn't always do, but that's kind of an area because lots of work recently and since we did our work, so that's something that we tried. And there are also sometimes more mundane ideas that can push the performance by 100%, and then when you add them up, you can end up with larger gains. But I think the question is that interesting or not? I think it's interesting if you get large in the end, a large fit in predictive power. But for this problem, I'm not sure whether we'd be interested in getting 1% better at least. But there are definitely things you can do that make the network better. Like we didn't spend a long time tuning this network, basically. Another question I think is, can we predict the dynamics directly? So do we need this ISO configurational ensemble? How much do we need it? And can we do something more generative maybe, where you predict configuration at the target time given the current configuration? And that's a scenario that has lots of work. Whether that's doable or not is whether there are kind of things which are interesting to the system that make it not possible, I think is an interesting question. Another avenue would be to kind of accelerate classical simulations. So use that to do jumps in the simulation and go further in the so accelerate the time step of classical simulations and mathematical simulations. I think an interesting word that appeared after ours is to use this for design and optimization. So there was this work on trying to optimize for plastic resistance. Here the idea was to design a glassy system and try to have it have specific properties under shaded information, and they were using a graph network to kind of as a lens that predicts this plastic rigidity. And so you could put that in an optimization loop where you would try to modify your system, then query the network for what's the propensity of the system, and then change your system again and iterate that way, optimizing results. And then last question is probably the most relevant is can we learn more about the physics? So and here we can I'm very happy that we can link to new work that answer or start to answer some of these questions. So can we distill down the predictors of the network to exhibit features? So I think that's a very good way to kind of say what is the network doing. If you can reduce, if you can get the same predictive power with attractive features, then I think that's one way to explain what the network is doing or is possibly doing. You never know whether it's doing some computation. Can we extend and tighten the study of the correlation links? So what we were doing here was pretty ad hoc. And it's not exactly the definition you want to use typically. So, and we were looking at the Chi4 with this system. The results were pretty noisy and pretty hard to. I mean, there was some signal, but it was not perfect. And the results are present here were a bit more convincing. But there's recent work that does I think a much better job at that. Another question I think is, can we learn something from whether this networks generalize or not? So I mentioned that we had good or decent generalization across temperatures, at least in the lower range of temperatures. But is there something to be learned here? Would you, if you can challenge a high temperature and try to predict at low temperature, does it tell you something about your system? Is it surprising or not? Or do you expect this to break at some lower temperature? And then finally, that's something I was always curious with this, is like, for these results, we have this higher upper bound limit, which is based on the variance of the displacements, which tells you how well you can predict this propensity, because it's only based on the finite number of samples. And then we have the prediction from our network. But yeah, I mean, it's a bit of an abstract question, but I think there's a bit of question of complexity. How well could you predict, if you trained an infinitely powerful, like the best network you could train, or how much can it cover, or what part of the dynamics is accessible to it, and is there a part which is going to be ultimately too complicated to compute or to predict? Or how does that compare to the complexity of your network? If that makes sense. Yeah. And that was my last slide, so thanks for the attention.
Thank you very much, Victor, for this very nice talk, and particularly for this future direction slide. I think we will discuss it in the discussion workshop after these 2 days. So I will try to do a small question round. I don't know how it will work, whether you will hear the questions, but let's just try it. So does anyone in the audience have a question? Okay, Miguel, just try to talk, or otherwise you have to go to the laptop.
Okay. Hello, can you hear us?
Yes, a little bit, yes.
Okay. Okay, hopefully now better. It was just a short question about, like, if you could tell us more about the generalization of your networks. Like you mentioned it at the end, like that you tried different temperatures and so on. Like, what else have you tried, or what do you think it is the cases that they don't generalize and so on? Hopefully you hear. Okay.
Yes.
Okay. Great. Thank you.
Okay, so I have to remember. I think temperature was the main one. I think there was a slightly different question at some point that we looked at, was whether we could predict different timescales with one given network, but I think that's going into a different direction. Although I think the question was, can you reuse some of the computation if you look at different timescales? So if you it's not like I don't think so you don't expect pure generalization there, because you would of course the targets are different, but can you use less parameters and have a single core chunk predict, do some basic computation on dynamics, and then you have a smaller network at the top that would decode things for different timescales. So maybe around 2 alpha you can adapt your prediction. So that's something we looked at, and I think we had decent evidence that we could do this kind of reuse. If you look at a range of timescales around the target timescale. Yes, I think the generalization. There's also a question about that there are some obvious. Like when you do generalization, it's always a bit of a tricky question. Like if you just train your network on this particular covariance mixture, then of course it's never seen anything else, so it's not going to generalize out of the box to other systems. But maybe the question there would be, does it? So you need to kind of think about the right generalization modes. You need to have some diversity in your training data, and you need the generalization to be out of distribution from your training data, but sufficiently close. So we haven't looked at these things, but I mean those are things that could be looked at. We'll let that be. I understood the question better.
I actually have one question concerning your denoising generative setup point. The problem is the moment you learn a network from actual dynamics, what the network learns if you learn over many configurations is actually the either configurational ensemble. So how would you do the denoising to kind of take that out? Do you have any specific idea, or was it just a generic thought?
So I think what I have in mind is that you could train a network. You could do a more dynamical, process where you train a network on a sequence of steps, and you train the network to predict, from a given time what's the configuration of the time later on, and apply that sequentially, and whether you can use that to make predictions which are not now predicting, the mean displacement at a given temperature, but some typical evolution of the system. So you could, and if you break down the dynamics and enough, then you can train your network in that regime. So you can, rather than training directly to go from 0 to alpha, you break down this as a sequence of predictions.
Okay, thank you.
So, Victor, I have a question actually that I asked yesterday already to Laura, and almost the same, the same level of accuracy. So
Yeah.
what do you think one should, can one get actually the GNN to do better? Do we need more data to get there is a part of the GNN that is not used for capturing anything in the sense that can it do it? So if you have much more data, you do it, or
Yeah, I think yes. So yeah, I think it's a very interesting question. So data, I think again, I think have a plot somewhere in the training. So we look at the performance as a function of data, and I think we were already pretty saturated. So I don't think that it would make that wouldn't be the solution alone. I think the recent work on that, the latest work I mentioned on GNNs, where they train with also edge feature predictions and get a big boost, is an interesting one. So that's saying something about training conditions. And I think that fits well with the story with like these handcrafted features as well, where you can imagine that the network is very powerful, it is very complex, but it's not hard to learn something complex, like if you don't train it well. And I think there's something about thinking about what's the right target for training, and how do you make sure that the network is encouraged, before it starts all of it, how do you make sure it's encouraged to do something non-trivial and something that can be predicted. And if you do that, then I think that's a way to kind of improve. The other part is like the thing I mentioned on like equivariance and having something a bit more, you could do things more fancy than what we have, which is pretty basic and which is not very well adapted, which doesn't have, like the network is not geometry aware in any sense. It's a very geometric network you apply to other problems, and so that would be another direction, which is very, theoretically makes perfect sense, and it's something you should have, and definitely would want to do in practice. My experience has always been that it's not as easy, and for the reason that I just mentioned, that it all depends on how you train it. You can train something very fancy if you're not careful about the training regime and the training data. And if you have noise in your training data and so on, then you might revert to doing a very much simpler computation.
Thank you.
One last question. Okay, two questions. We don't want to have a discussion.
Well, okay, so maybe this is more along the line of discussion, but what I can you hear me? You can hear me? Yeah. Okay. So what I have never quite understood is we know that there's a dynamical correlation length, right, which is growing as you go in time, right? So for example, if you want to compute things a time tau alpha later, there's quite a large dynamical correlation length by that time. And why does that? I guess maybe this is what Gerhard's going to talk about. But why does that not affect the distance over which you need to, the size of your graph neural networks? How many shells you need in your graph neural networks?
Yes, so the network has a natural, receptive radius, which is the distance between two atoms connected by an edge times the number of times you apply the network. Basically gives you, the size of, where it can look at. And in our case, that was, as large as the system size. So the network could effectively, look at the full box, which means that, if we had a problem with, kind of simple question correctly, if we had, the fact that if the dynamical length was getting, close to like what the network would compute, we would have, boundary effects as well, because that would mean it's switching the size of the box. But there is, if you have a, there is a direct, there is a very explicit bound you could make on like what the network can compute versus the, maximum length. So if the length goes beyond, 5 times or 7 times, Turing's term in our case, then then you'd be in trouble because then you couldn't make any computation beyond that. But for those systems, the lengths, that we the length that we extract, like the correction length we could extract from our network was much more limited, so it was far from like this upper bound. That answers the question.
Okay, one last question from Hayato Shiba.
Just a question for interest. And do you expect? Can you expect anything which would exceed GNN? I think you are a data scientist, so I would like to hear any view from you whether any potential new neural network models can be possible, or do you think? How do you think in the future?
Yes. Thanks for the question. Yeah. So I mean, I guess the answer always has to be yes, right? Like the work of like the graph, glass MLP, is showing that you can exceed all performance with a much simpler model. So I think it would be a bit foolish to say that cannot be anything else. Then, but there are not that many. I mean, I guess from the main perspective, the big thing right now is like what people call transformers, which are kind of more just still relational networks that can think about relations with an object, but we don't have this notion of the graph. It's an all-to-all version of the graph network if you want, where every node can share information with every other node, and then have a mechanism for attending between nodes. And this is kind of sweeping, like this is solving a lot of problems at the moment. This is the best architecture for a lot of problems, and a lot of places where graph networks are being used. Now for this type of, I think in that one you have such a strong bias for like locality and sharing information. Like what the connection, what the graph is, like what the nearest neighbor graph is, and I think that still gives a lot of advantage these approaches, these approaches to an explicit graph. So yeah, and I think whenever you try, on this type of problem, the more you look at this type of problem, the better a graph network perform compared to other approaches.
Okay, thank you very much, Victor. And yeah, let's thank Victor again. And we will now have a coffee break and we start at 11.
Thanks, Holger.
Il est en Allemagne pour une autre conférence. The failure of the whole machine learning field. Well, no, I'm going to talk about a very specific application of machine learning. So I will try to discuss whether machine learning can be used to sample glassy problems. So this is work in collaboration with Simone Sarella, Jean Tranquier, and Martin White. And we have a preprint that is going to be submitted soon. So if you have any feedback, please let us know. Also, I wanted to acknowledge many useful discussion with Marilou Gabriel, who is in the room and gave us a lot of ideas and inspiration for this work. So, okay, what's the motivation? So the idea is, okay, you want to generate equilibrium samples from some Boltzmann distribution. And we know that a universal strategy to do that is to use local Monte Carlo Markov chains. So you try to flip a spin or to change, to displace a particle. You accept the move with the metropolis weight, for example. And well, of course, we know that there are problems, in particular glasses, for which this strategy doesn't work very well at low temperatures. The local Monte Carlo gets stuck. And so the problem is hard to sample. So in particular, there is a class of problems which are mean field glasses, for which you can prove, even rigorously, so in that paper, that there are non-trivial correlations between variables. These are called point-to-set correlations that hinder local decorrelation. So when you try to flip a spin or to move a particle here, there is a strong correlation with the surrounding spins or particles that basically prevents your particle to move. And that's why the local Monte Carlo fails. Now, we know that there is hope, in particular because of the swap algorithm. So, but this is okay in 3 dimensions. So, well, the idea is to swap particles, and we know that in this way we can have a massive speed up. And we also have a paper from some time ago where we showed, for example, that if you take a glassy problem, a mean field glassy problem, but it's a very specific one made of plaquettes, you can actually make a non-local change of variables. So if you are smart enough that you can detect this, well, we're not smart, we knew it in advance, but I mean, if for some problem you are smart enough that you can find a non-local change of variable that makes the problem non-glassy, then maybe you can sample it easily. The problem is that these things are kind of system specific, so you need certain properties of the system to use them. So then there was this idea that maybe machine learning could provide a kind of universal solution for this problem. And the idea is the following. So suppose that you can find some auxiliary distribution, which is some generative model that represents a probability distribution P of sigma, such that it's a good approximation of the Boltzmann distribution. So for example, the Kullback-Leibler divergence is very small, which means that your probability distribution is very close to the Boltzmann one, and also that you can sample easily. So for example, you can take an autoregressive structure. So the idea of autoregressive models is that you decompose the probability distribution into using the chain rule. So you write it as the probability of the first variable, then the probability of the second condition to the first, and so on and so forth. This is of course exact. And then you can learn a model for each of these conditional probabilities that approximates them in some way. So there are many architectures that you probably know better than me, and I will come back on that. So suppose you can do that, then you can use this auxiliary model in a kind of Monte Carlo scheme that we call global Monte Carlo. And how do you do that? Well, you propose a new configuration from this auxiliary model, and this is easy by definition because the model is easy to sample. And then so at some time you are in a certain configuration, you propose this move and you accept with the metropolis weight which now is takes into account that you generated the configuration from this auxiliary model. It's very similar to importance sampling, so where you sample from the autoregressive and you just reweight your samples with basically this weight, this ratio. Here I write it in a Markov chain just to make it more easy to compare with the local Monte Carlo. So okay, so that's the idea, and well, this will work if, first of all, this weight does not fluctuate wildly. What I mean is that if, for example, these objects are typically exponentially fluctuating with n, they are exponential of quantities that are of order n, where n is the number of variables. So if this thing is exponential of n times something that is fluctuating, well, this will fluctuate a lot. And when n is large, you are going to basically reject all the moves, so you don't want that. So you want this to be somehow close to 1. And also, what you want is that your auxiliary model covers well all the space that is the support of your target distribution, because otherwise the moves that you propose are going to be kind of localized in the space of configurations. And both conditions are satisfied if the Kullback-Leibler divergence is small. I will come back on that. So the idea is, okay, maybe I can learn the auxiliary model by minimizing this Kullback-Leibler divergence. And this is something that was explored in these papers. And well, now, of course, I mean, in order to compute the Kullback-Leibler divergence, what you need, I mean, the Kullback-Leibler divergence is basically the average of the logarithm of this reweighting factor over the Boltzmann distribution. So the problem is you need to sample the Boltzmann distribution to compute it. But sampling the Boltzmann distribution is the problem you want to solve. So people started to think about possible ways to bypass this problem. And there are several solutions that have been proposed in the literature. So I'm going to discuss 3 possibilities. So the first one is, okay, let's assume we can sample. Of course, we want to sample, but let's assume, I mean, let's take a case where we can sample from the Boltzmann distribution. Then we can learn the auxiliary model by minimizing the exact Kullback-Leibler divergence. And this is a way to test the expressivity of the model. So if this works, if the model works, well, that's the best case scenario. I already know the solution, but at least I can test if the global Monte Carlo done with this auxiliary model is able to decorrelate and to sample properly. So that's a kind of test setting, let's say, for the model. Then in a more practical way, what you can, there are 2 main ideas I think that have been proposed. One is to use the other Kullback-Leibler divergence. So you know the Kullback-Leibler divergence is not symmetric. So if you reverse the 2 models, here what you get now is again the logarithm of the weight, but now is averaged over the autoregressive or the auxiliary model. And so now this is easy to compute because by construction you can generate samples from this model easily. Okay, so this is computable, and you can also show that this Kullback-Leibler divergence is actually the difference in free energy between the 2 models. And so we know this is basically the variational principle of statistical mechanics. The Boltzmann distribution is the one that minimizes the free energy. So, well, if you cannot minimize it, at least the free energy of this auxiliary model gives you an upper bound to the true one. The problem with this is that, well, now if the auxiliary model is very close to the target one in some region, but it gives 0 probability to some other region, as you have in this example. So if you have, for example, 2 peaks in the real distribution, and the auxiliary model only learns 1 of them, well, this quantity is still going to be small because this part, the part that has 0 weight in the auxiliary model, will get 0 weight in the calculation of the Kullback-Leibler. And so this quantity is still small, but your model is not very good because it's only learning 1 part of the space of configurations, which is not the case in the previous one, because that one is averaged over the true distribution. So in that region, the Boltzmann distribution has a non-zero weight, but the logarithm of PB divided by PR is infinite, so that quantity would be big. Well, so, anyway, you can hope. So you have this problem. This is called mode collapse. But you can still hope that it doesn't happen. So that's a possibility. The other possibility is to do some kind of simulated tempering. So the idea is, OK, I cannot sample at low temperature from the Boltzmann distribution with local Monte Carlo. But so let's try to start at high temperature. So at high temperature, I can sample from the Boltzmann distribution. I generate a sample. Now I learn an auxiliary model from this sample. And then I lower a little bit the temperature, and I use my auxiliary model to generate a new sample, but now using the global Monte Carlo that maybe is faster. And so I learn a new sample at a slightly lower temperature. I train again the model, and I keep slowly lowering the temperature, and I hope that the auxiliary model is learning enough to keep the global Monte Carlo efficient. And so in this way, I can go down in temperature and reach low temperatures where the local Monte Carlo would be stuck. And well, in the paper of Marilu, there is also a slightly different scheme that also, I mean, follows similar ideas, but in a different implementation. And we tested both. Now, what are the kind of architectures that we use? I put this picture, but actually the simplest thing you can think about is a shallow MADE. So a shallow MADE is basically a one layer with a softmax after it. And well, in statistical physics, it's just a Boltzmann distribution. But you see that, for example, the first spin, if I'm thinking to Ising spins, the first spin has just a local field. The second spin has a local field and the coupling to the first spin. But now I have to normalize it, because now this is normalized on the second spin. So this will give me some kind of many-body interactions because of this denominator, OK? So the numerator, when I multiply all these probabilities, the numerator is basically the usual two-body Boltzmann thing. But then I have these denominators that are making the difference. And this is also why I can sample easily from this. These additional architectures, well, either you can put more layers. So instead of just here you are applying. So what you want to do is, given the first k spins, you want to predict the probability of the k+1 spin, right? So you want to train a network that takes the first k spins as input and outputs, for example, a number which is a local field on the k+1 spin. So what you can do, here you are just applying a linear transformation to the input and then taking a softmax. What you can do is stack many layers. So you do as many layers as you want with nonlinearities and whatever you want, and then in the end you do the softmax. The NADE is basically the same idea, but you share some weights to reduce a bit the number of parameters. And well, we thought, OK, maybe because we studied problems on graphs, we thought, OK, maybe we can exploit the graph. So we also considered a graph neural network where you take your graph, you first process it using a graph neural network, and then you put that into a MADE. It didn't really change the results, but I will show you more. OK, so why we had hope that this could work? Because there was a paper from 2 years ago where they applied this idea to the two-dimensional Edwards-Anderson spin glass, which is a glassy system. So it's, for those who are not familiar, you have n Ising spins plus minus 1. And the Hamiltonian of the system has just two-body interactions. So the spins are on a two-dimensional lattice. Each spin is interacting with the four neighbors with a coupling Jij, and the Jij are Gaussian random variables. So we reproduced this work. So these are our results, but they are the same as the one in the original paper. And so this is simulated tempering. So we start from temperature 1. So at temperature 1, local Monte Carlo is very fast. You can see here this is the correlation time of local Monte Carlo. When you reduce the temperature, it goes up. So this is the scale, OK? So it goes up. In this model, there is no phase transition at finite temperature, so it's going to diverge only at 0 temperature. But still, here it's becoming quite slow. So the dynamics is slow and glassy. And so what we did is we start by generating a sample at temperature 1, where the local Monte Carlo is very fast. We train a model. So in particular, we took this one, the shallow made. And so we train this model, and then we lower a little bit the temperature. We run the global Monte Carlo using the model we just learned. We generate a new sample, and we keep going. So what you see here is, for example, the energy of the model that we learn compared to the energy that we get from local Monte Carlo. So here, the local Monte Carlo is still doable down to 1.5, so we can compute the energy and we can compare, and it's very good. We can also compute the entropy by integrating the specific heat when we go down in temperature. And we can compare it with the entropy of the model that we learn. That is easy to compute because you can sample and then you can just average the log of the probability on the sample that you generate. And you see that the entropy also is very close, which means that there is no mode collapse. So the entropy is really the same. The two models have the same entropy, so they are spread over the same space of configurations. And also here, I mean, from these two, basically you can get the Kullback-Leibler divergence, and you see that it's quite small. This is the total Kullback-Leibler. And here we have 100 spins. And as I told you, this object is naturally of order n. So if you want to have some intensive quantity, you should divide by the number of spins. So you see that it's a very small number. So the two models are really close. And indeed, you can see that the acceptance rate, this is the, so when I do the global Monte Carlo, I propose moves from the model that I learned, and then I accept with this probability, and this is the average of this acceptance probability, the inverse, because basically whenever you, because the autoregressive model is spread over the whole phase space, when you propose a new configuration, it's going to be essentially uncorrelated from the previous one. So if you accept the move, you are basically decorrelated, okay? So the relaxation time of the global MCMC is basically the inverse of the acceptance rate. So that's why we plot the inverse. And you see, this is the right scale to look at. It's of order 1. So you accept one move every 1.5. And it actually goes down with temperature. So it becomes even faster when you decrease the temperature. So this is very good. Because basically, when you are at this temperature here, you get a huge speed up. You can, in terms of computer time, it's about 5 orders of magnitude speed up with respect to the local MCMC. So we are happy. One important thing that is going to be important for the next part is that in order for this to work, here we have 10 to the 5 training samples. So we start at temperature 1 with 10 to the 5 samples generated from local MCMC. And then when we do the simulated tempering, each of these 10 to the 5 samples is evolved. Okay, so we always have 10 to the 5 equilibrium samples to train the auxiliary model. And actually, this is needed. I mean, if you reduce, this is the dependence of the acceptance rate on the training sample size at temperature 1. And you see that you need 10 to the 4, 10 to the 5 samples. If you reduce the training sample too much, then you start to have a very low acceptance rate, and things don't work well. Okay? Okay, now we said, okay, well, this is promising. Let's try a different problem. And the motivation was that we know that glasses are actually not in the same universality class of this model. Glasses are harder, at least in field, but probably also in 3D. And glasses belong to this, at least in field, belong to this random first-order transition class that Olivier introduced yesterday. So what you can prove, again, rigorously in mean field, is that the sampling time of local MCMC is finite at high temperature, but it diverges as a power law when you reach a certain transition, that is the mode coupling transition or dynamical transition. And below that, it's exponential in the size of the system. So we wanted to see, okay, can we use this idea to speed up sampling in these problems? Maybe it will still be, I mean, our hope is maybe will still be exponential in n, but maybe with a smaller prefactor, and things will be a bit better. So okay, we wanted to find the benchmark. There are many models in the RFOT class. So we chose one. Why? So first of all, we wanted to have two body interactions. So we wanted to consider a spin model, because if you take a particle model, well, you have to go to high dimensions, then you have continuous variables because the particles are continuous. So when you want to build an autoregressive model with continuous variable, I mean, things get more complicated. So we wanted to be in the easiest possible case. So we took a spin model, and we wanted to have two body interactions. And the reason is that we wanted to use this kind of architecture for the MAID, for the auxiliary model. And this is, I mean, this naturally has two body interactions. You could add three body interactions, but then you would have more parameters and so on. So we said, okay, let's stick to two body interactions. So the easiest model in that class with two body interactions is the graph coloring, which is also a well-studied problem. So we thought, okay, this is a good benchmark. So how does it work? You have a graph, which is a random graph. So that's why, I mean, it's an in-field problem, because the graph is random. It's not a 2D or 3D graph. It's just a random graph with sites being connected at random with a certain probability. And on that graph, you put colors. So you have variables that now are not Ising variables, but POTS variables that take Q possible states. So the Q states are the Q colors, red, green, blue, and so on. And then you have a Hamiltonian, and the Hamiltonian is just you pay a penalty 1 whenever a link has the same colors on the two sides. So if you put two red spins on that are connected by a link, this costs you energy 1. Otherwise, the energy is 0. So this is a well-studied problem, and what we know is that it's not always in the RFOT class. Sometimes it's more like the spin glass. So in order to have a strong, let's say, RFOT system, you need a large enough number of colors. So we took 10, that was the minimal one, to have a good separation between the different transitions. And well, now if you look at the phase diagram for 10 colors, so here you have the connectivity of the graph, and here you have temperature. So you have two transitions. The blue line is the dynamical transition, where the sampling becomes hard, and the red line is the Kautzmann transition, where you go into an ideal glass. So in order to get some hard sampling region, we need at least connectivity 40. So that's what we chose. So for connectivity 40, we have a dynamical transition at temperature 0.17. So below that temperature, it's exponentially hard to sample in N. And there is no Kautzmann transition, which is good, because it means, this is technical, and I'm happy to discuss it later if you want, but it means we can use a technique called quiet planting that allows us to generate one configuration, one equilibrium configuration for the graph. So at least we have, given a graph, we have one equilibrium configuration that we can use to start the local Monte Carlo and to check the equilibrium local Monte Carlo dynamics. So the system size is 250. We needed a large enough system size because the connectivity is 40. So in order to be not so far away from the thermodynamic limit, we wanted to have the system big enough, but we couldn't make it much bigger because then it becomes too hard. So this was a good compromise. So and I wanted also to point out that the thermodynamic limit in this model is exactly solvable via the cavity method. And for example, there is a lot of work from Florent Chakala and Lenkas Deborova, who solved it. And I mean, basically, this phase diagram is taken from their paper, essentially. What you have in the inset here is the relaxation time of local Monte Carlo. So you can see that indeed you have a power law divergence at the predicted temperature. So this is, I mean, we checked it. We have some finite size effects, but okay, 250 seems to be not so bad. In any case, it's lower than the... Okay, now the first step was, okay, now we want to repeat the same thing that we did for the spin glass. So the first step is to select a model. So what we did is to take temperature 1. We generate a sample from local Monte Carlo, which is fast at this temperature. Remember that the glass transition is at 0.17. And then we considered many different architectures. And what you see here is the energy. So we trained these models by maximum likelihood on the sample that we have. What you see here are the energies So this is the equilibrium energy that you know, and these are the energies of the model. These are the entropies, and these are the Kullback-Leibler divergences. There is a lot of information. You don't need to look at all of it. The models are sampled from top to bottom in order of free energy. Free energy at temperature 1 is just energy minus entropy. And so the only important thing is, OK, there are two models that are good. And these are basically the shallow made, so the same one, I mean, the one where you do this. OK. So this seems to be the best models in the class that we tried. You need to have enough training data to get this. If you try to put regularization, so for example, dropout or ridge, well, what you see is that the entropy increases and the energy also increases. So it doesn't seem to be good. If you try to increase the expressivity, so you put more parameters, again, it doesn't seem really good. And also, in some cases, you get, for example, here you get a too low entropy. So it seems that you are kind of overfitting and you get mode collapse. Yes?
Sorry, Francesco, I'm a bit lost there. Why is the energy increasing? You're doing the Boltzmann reweighting, so it should always give the right solution.
No. Sorry. Right. So this is the energy without the reweighting. So we just want to test how well the model is learning the true one. Right, if you do the reweighting, then it should be the same. But so the problem is if you put dropout, for example, if you put regularization, what happens is that the model tries to have a bigger entropy, but also sacrifices the energy, and so it doesn't look good. So in the end, we took these two. So these are the shallow made, trained in two ways. One is minimizing this Kullback-Leibler, and the other is minimizing the other Kullback-Leibler. So one is maximum likelihood, and the other is the variational one. Now, OK, what happens when we lower the temperature? So here you have the energy and the entropy of these two models. So now what I'm doing here is I'm lowering the temperature. For the maximum likelihood model, which is the orange, at each temperature, I'm generating a new sample by local MCMC, because still here the temperature is not too low, so I can still do local MCMC. And at each temperature, I relearn the model on the sample. So that's the ideal setting. OK, that's the best I can do. In the other case, the purple one, I'm doing the variational training. So I'm using the reversed Kullback-Leibler. So in that case, I don't have to sample from the model. The problem is, as you see, so the problem is that the maximum likelihood is when you lower the temperature, it keeps a good entropy, but it's not able to go down enough in energy, while the variational one is able to fit the energy well, but at the price of reducing the entropy. So it's kind of mode collapsing on some. So because the distribution, the Boltzmann distribution, when you go down in temperature, is starting to have all these local metastable states that give you local peaks of the probability, and probably the variational model is trying to learn some of them in order to keep the energy low. So that's what we see. The other thing we did is, OK, I told you that we have equilibrium samples. So this is the local MCMC dynamics, starting from these equilibrium samples. And what I can do is also to generate samples from the autoregressive models and run, again, local MCMC starting from those samples. And what we see is that for the variational model, the two dynamics are quite similar. So it means that the variational model is generating configurations that are still close to the equilibrium ones, even if just a subset of them. While for the maximum likelihood, the two dynamics are becoming quite different. And this is the ratio of relaxation times. You can see that the variational one is tracking very well the divergence of the equilibrium, while the other one is faster. So I have 2 minutes, right? I'm going to finish. So what's the problem we found? OK, the variational model is mode collapsing. And this, I think, is at this point is quite clear. I mean, the entropy is going down. And also, now if you run global MCMC using the variational model, what you see is that at some point, the correlation doesn't go to 0 anymore. I mean, shouldn't go to 0, so it should go to 0.1, because 0.1 is you have 10 colors. So if you take random configurations, the correlation is 1/10. But so you see at high temperature it works, but when you go low in temperature, still quite higher than the glass transition, you propose moves that are only in some subset of the space, and so the correlation doesn't decay anymore. And also, you could say, okay, maybe I cannot use it for global MCMC, but maybe I can still use it to generate configurations that are close enough to equilibrium that I can at least get some idea of what is the equilibrium dynamics. But even that doesn't work. I mean, at temperature 0.2, unfortunately, you start to, I mean, the energy starts to become higher, and you start to generate configurations that have a dynamics. This is local dynamics that is faster, and then you see aging, and the dynamics slows down, so you don't gain much. The maximum likelihood has a different problem. So recall that this is the best we can do for a given architecture. What happens is that, well, if you fix the temperature to 1 and you increase the training set, as in the spin glass I showed before, the acceptance rate goes up, so that's good. But then when you lower temperature, it goes down exponentially. So this means that if you want to lower the temperature, you need more and more training samples to get a decent acceptance rate. And well, you could think, okay, maybe I can use more expressive models to have a better fit, but this would probably require even more training data. So I mean, we didn't find, I mean, the conclusion is it doesn't work, and we didn't find a clear way to move forward. I mean, we didn't, because if you try to use more expressive model, you get overfitting, and then maybe you have to increase your training set, maybe exponentially in temperature. If you try to put some regularization, then you lose in entropy, and I mean, you increase too much the entropy and you go into the underfitting. And so maybe, I mean, my feeling is that there is something that is maybe an intrinsic limitation of this structure that we chose. Because you see that here you start by sampling one spin, so then you sample the second condition to the first, and so on. But so if you have a system with a lot of constraints and many different peaks, then maybe you cannot learn all the probability peaks in this way. It's possible that maybe a better architecture could do the job, but we didn't have any idea. So if you have ideas, well, what we are trying to do now is to, instead of learning one model like this, try to learn like a kernel that can propose moves. So you learn a function k sigma sigma prime that proposes a move given the previous one, because here you are proposing a move without taking into account where you are. There is a paper that that did again the spin glass using this approach, learning moves based on the current configuration, and it seems to work quite well in that. I mean, not amazingly well, but seems to work in that case. So it should be worth to test it. And also one thing that we would like to do is to try a lattice model in 3D to see if maybe there is something specific of the mean field. So we are trying to look at a lattice glass model in 3D to do it again. And that's it. Thank you.
Questions?
Thank you very much, Francesco, for the great talk. I was wondering, yeah, very interesting that you tried all the different things, just running a global Monte Carlo with either one of the models trained by variational inference or the maximum likelihood, and also that you tried generating a configuration and then having the local equilibration from it. I was wondering if you had tried doing something where you interleave global steps and local steps, because in my experience, it's something that maybe with the variational inference, you only look at a subset of the configurations, but then you have the local moves that allows you to explore, and then you can jump again thanks to the fact that the local move is putting you in a nice other place. I mean, this feels like it can make a difference. Have you tried?
We did. I mean, thanks to your suggestion. I didn't have time to discuss it, but I mean, we didn't. It didn't work. Maybe we didn't. I mean, there are some parameters that you can tune. Maybe we. I mean, if you have any idea, we are happy to try again. But the problem is essentially that the local moves. I mean, when you go to low temperatures, the local moves are not going very far away, and then the global. I mean, basically, what you are doing in the scheme that you propose is to combine these two things. So you do a bit of local moves, and then you do, from time to time, you try to use the model to make a big jump. But the problem is that in our, when we tried, the big jump is not accepted, essentially, because even in the best case, it's not accepted. So when you, and the local moves don't go very far away. So it's, I mean, in our implementation, it didn't work. We should keep trying, probably, and just.
And if and were you retraining, or were you just training first?
No, we were retraining. So we were doing. We really used your scheme.
Okay,
so we started with the. We start from. I think we started from the variational, maybe. So we started from the variational, I think, but that's mode collapsed. But then we use chains that are a bit everywhere. Then we run the.
Because I guess the intuition could have been that okay, you have a large sample size, but you still visit regions you haven't seen, and so you cannot. I mean, when you are in a region you haven't seen, the global model is maybe you cannot jump out of a configuration, and so if you were retraining, then you now.
Yeah, we were retraining.
Okay,
so I think we also tried to do a combination of simulated tempering. So we start from high temperature where the model is well spread. We go down in temperature, we do a combination of local and global, and we retrain, and still it's stuck.
Thank you.
Other questions?
A very naive question, because I'm not sure I understood everything, because I'm not really from this field, but in the case where, I mean, you say it doesn't work, so if I understand well, okay, when the problem is big enough and there are a lot of local minima to find, what is the best hope you can have? I mean, right, if there is, I don't know, 10 billions of local minima to find, isn't it normal that it takes, I don't know, more training data or more compute time, even with the smart method? Because, right, you have to find them all and represent them all. So
well, maybe you don't need to find really all of them. You could hope that you can find a representative set of them. And this would be enough to
typical set, like
some typical set. And I mean, even even if you are able to learn one of them, you could generate. It could be a way to generate one glass at least, even if you cannot generate all the exponential complexity of all possible glasses. Even if you could sample a few of them, but the tip, even one or two or whatever. But it's like when you want to produce an ultra-stable glass. You are happy even if you get one. You don't want to sample all possible. So even if the model were mode collapsed on 1, 2, 10 glasses, but the right ones, I would be happy, because that would be a way to study very stable glasses in a. I mean, we know how to do it with the swap or with vapor deposition, but this would be a universal way of doing it. So it would be wonderful. The problem is that the model, when you go to low temperature, is mode collapsing, but also it's mode collapsing on bad glasses, on high energy glasses, essentially. When you push it to.
So you said it's work in progress, but can you say something about the lattice glass in finite dimensions? Because I mean, you started by saying glasses are different from the 2D Edwards Anderson, but as soon as you put these kind of models in finite D, all signatures of the MCT crossover is totally gone. So if you put this in finite dimension, don't you think it's going to be super efficient?
Maybe so.
What are the initial
it's not even work in progress. Is an idea we started talking about it like a week ago. But we wanted to take the model of Yoshiyuki and the 3D lattice glass that seems to be a good one, and try to repeat exactly the same study. So in principle, it's straightforward. We have all the codes, so we just have to rerun it. But
because here you have many tools, like
sure.
You can do swap, a little bit of swap, which is helping. And I mean, we are looking at the dynamics of that model, and you see nothing of the MCT transition.
But you still have a slow dynamics.
Yeah, it's slow, but maybe it's just.
Maybe it's slow. And
then it's the 2D thing, and then.
I agree. So I want to try it. So we'll do it. I hope in a few weeks we should have the results. I mean, the pipeline is there, all the codes are there, so it's just a change of the model. So, I mean, we took a lot of time to, I mean, because we did many efforts to make it work for the coloring, and we were a bit fixed on the coloring because we thought it was a good benchmark. Spent a lot of time on that, and then we thought, okay, maybe now that we have done this, maybe we can try other models. So I agree. I mean, that's related to the question of whether glassiness in 3D is due to really these big point-to-set things that make it really hard, or it's maybe a more local thing that you can more easily learn. So it's worth trying.
Other questions?
I'm wondering if there's some middle ground between just completely using machine learning to come up with this and doing something that's more physically motivated, like Monte Carlo swap, you know, where you can understand the physics of why swapping these two would help. And is there some way to put some physics into the models you're trying instead of doing it completely with machine learning? Have you thought about that?
Yeah. I mean, for the coloring, I don't see, I mean, I don't think anyone has an intuition of, I mean, these are really correlations that are subtle and you don't see them. So I don't think, I mean, of course, for the coloring, there are there is a big community of people who has been trying to develop smart algorithm to find, for example, ground states. And there are no smart moves that you can see by eye. So that's why we took it as the hardest problem. Now, I agree that maybe for problems that are not as hard as that, you can maybe find if you have some intuition. So, but then I think it's a bit system dependent. So one should decide on an example, and so maybe these lattice glasses are, because then you can maybe also tune for example, change the space dimensions as usual, and go from a situation where maybe you have intuition on the local structure of defects to a high dimensional case where it becomes more like the coloring. And so yes, so this would be a bit along the line of the work that you did with Sean on the changing the dimension and see whether the softness remains a good predictor. And so yes, we will do.
Other questions?
So you said it's complicated to go off lattice or continuous. Like, is it very complicated, impossible, or is just technicalities?
Well, yeah, maybe people in this room know better than me what to do. The problem is, I mean, if you are off lattice, well, first of all, you have to decide, you know, when you do these autoregressive things, you have to decide an order. So if things move around, maybe also I mean, in these cases, the order is not very important, so you could choose a random one, but maybe when you are, because, for example, you could decide that your degrees of freedom are the particles, then in an autoregressive architecture, what you do is, okay, first I learn a distribution for one particle in a simulation box. So, okay, there will be some local potential that is probably going to be flat if the system is homogeneous. Then you want to learn the distribution of one second particle conditioned to the fact that there is already one particle in the box. Well, this will be probably a two-body potential. Now you want to add the third particle. So you see, I mean, it's doable. I think it's doable, but the problem is you have to discretize the box. You have to learn a local potential that is now a continuous. So here you learn one parameter for each probability or a few parameters, and if you want to learn a full potential, it's going to be heavier. But I don't see any, in principle, I don't see any problem to do it. I mean, you probably can parameterize these things in a smart way. I mean, basically, what you want to parameterize is the probability distribution of one particle, given that you already have k particles in your box. So maybe if you do, I don't know, some Fourier transform, some wavelet transform, some whatever thing, or if you use a smart basis of potentials, the problem is how to.
Maybe I just come back to Francois' question. So do you think there are inherent impossibility to make it work for a model like the one you studied, in the sense that if you have an exponential number of peaks, you know that you are targeting low energy ones, and then you start, I mean, you know that you have mode collapse. So I mean, how you can avoid, how is it possible? I mean, how is it possible to avoid mode collapse and go and targeting these states? So maybe they're exactly like we know, at least we think that, I don't know, for example, in these cases, some local dynamics will never go below, I mean, some energy. Maybe it's just impossible to find.
Maybe it's just impossible. I thought it was worth trying, but I mean, one thing that we did, also actually following a discussion with you, was to check what happens in the Curie Weiss, which is a ferromagnetic model with 2 states. And in that case, I mean, you can prevent mode collapse if you are a bit careful on imposing the symmetry or having a big training set and so on and so forth. And what happens is that this model, I mean, when you are in the ferromagnetic phase, you have 2 states. And the model can learn the 2 states, and it's quite easy. I mean, you first choose the first spin at random, but then the second has a strong coupling to the first. And basically, you keep putting strong couplings so that the spin, once you choose a state with the first choice, then you propagate it through the other variables. So I think if you have, for example, if you have a finite number of states, maybe you can learn it because you can select, you can use like the first k spins to select a state and then just propagate the choice you made. Now, when you have an exponential number of states, I think it's impossible, but again, you could hope to learn a subset of them that is maybe enough to, I would, of course, if you want to sample, to properly sample all the states with the right weights and so on and so forth, it might be impossible, but a less ambitious goal would be already to be able to sample a few of them.
Yes, I agree.
So maybe you can.
Yes, if there are the few of them that you want are the hard ones. So
yes. So for example, one thing.
You say the system collapsed, but on nodes that you don't want, you would
yes.
like to go to the other ones.
So I mean, a way to see that this is probably not going to work in the coloring is that, well, you know that when you do it at 0 temperature and you look for solutions, this is basically a kind of a greedy algorithm where you choose one spin at random and then you choose the second condition to the first. And we know that for the coloring problem, to find colorings, this works up to some point, but not in the hard region. But the hope was, okay, maybe if we are at finite temperature, the constraints are a bit softer, maybe we can do something. I mean, I agree that there were good reasons to think that this wouldn't work, but I thought it was good to try.
To show that, I mean, it works up to a certain level and then...
Yeah, I mean, if we can identify like a threshold, yeah, that would be nice. For the moment, we didn't really find a sharp threshold. You see, I mean, it degrades smoothly in temperature. It's not like, okay, it works up to this point and then there is something happening that kills it. So there is no phase transition, it's just a smooth... But maybe you should increase the size and...
Okay, thank you very much. We have to move on with the second talk.
Yes, sorry.
So it's good. All right, so now the floor is yours. It's Giovanni Volpe, digital microscopy with deep learning.
Okay, so thank you very much. So it's a pleasure to be here. I'm not going to speak about classes, which is a pity, but I guess the idea was to give a bit of diversity to the topics of the workshop. I will speak about digital microscopy and how deep learning helped us to improve it, and a toolbox that we have developed that is freely available that can maybe help you. I will also give some pointers about some ideas that came during the workshop. And I guess on Friday then I can give a 10 minutes presentation where I give my ideas about what could be tried out. There are many, many ideas that come out. I really like this workshop, I have to say, because what I really like, which is actually different than when you go to workshops more in soft matter physics, is that people here try the base scenario. So they don't just use machine learning because they can, but they really compare that with other approaches that are more standard, even when it turns out that they actually work better or equally well, in which case you should actually fall back to the standard approach. So that's really nice to see and refreshing in that sense. So what I will, and of course I would like to thank also Camille for giving the laptop, because my laptop cannot connect to the projector. I hope it will work, because this is the first trial of preparing a presentation on PowerPoint and run it on Keynote. We'll see what happens. Anyway, so first of all, microscopy. I guess all of you are familiar with microscopy, at the very least because it's a tool that you must use if you want to study glasses, colloidal glasses, and so on. And here I just want to give a brief overview of history of microscopy and particle tracking. So this is a very rich history that goes back more than 100 years, when actually Perrin, Frenchman, tracked manually Brownian particles. So this is very famous manual tracking of made by Perrin of Brownian particle, which actually, think about it, permitted Perrin to demonstrate that these particles were diffusing, and by demonstrating that, demonstrated that atoms existed. So think about it. 100 years ago, in this room, probably there were scientists already. They will not think atoms existed. They will think they were a nice mathematical tool to describe the reality, but they will not think that they were actual objects. Perrin convinced them by tracking particles manually, even got a Nobel Prize for it. Then people followed suit over the next 20 years. Things changed after the Second World War, because people started combining microscopy with electronics, very simple electronics. And this again comes from a very surprising place. The first mention of a combination of microscopy with electronics or electrical circuits comes from coal mining. And the reason is because in coal mining in the 50s they had a problem, which is that coal, if it's sufficiently, coal has particles that can go into the air. If you have enough of these particles, it can self-ignite, which means you can have an explosion. So it would be nice to be able to track this. And someone proposed to actually do this automatically through digital video microscopy, essentially. So that's the very first mention of microscopy combined with electronics. Of course, after that, people moved to use these tools in biomedicine and so on. You know, you have plenty of scanners and cell counters, and flow cytometry are actually different versions of microscopy combined with electronics. And very recently, in the, let's say, 90s, people started actually thinking about using digital video microscopy with colloidal particles. This goes back to the work of Crocker and Greer in the 95. And after that, there has been another revolution very recently in the early 2000s with the advent of deep learning. I guess I don't need to motivate deep learning to this audience, but that it's a new way of looking at data in microscopy, where we don't really understand what we are doing, but we hope that a computer can still do some task, even though we consider it as a black box. And in this story, we came very recently because we have now developed this, comprehensive toolbox for microscopy in deep learning called DeepTrack over the last maybe 5 years. Okay, so this gives you an idea of the history of microscopy and how deep learning fits into this history. And now with that, I would like to go through. I think I will focus mostly on the first part of this talk, which is essentially showing you some things that we have done and what other groups have done in combining microscopy with deep learning. And hopefully this can give also some ideas. And I will try to point, especially in the most advanced applications of deep learning, that I think there are ideas could be used also in the glass community, beyond just tracking the particles. And then I will give a very quick overview of the software and some essentially case studies. These are case studies for how to use the software. So it's very brief. Okay, but let's start with a simple example. And this is a simple example is essentially the example with which I started my journey into deep learning, and it's about particle tracking. So any of you who has done experiments with colloids or has used experiments with colloids most likely track the particles or had someone tracking the particles for them. And this practically means that most likely the simplest approach is to just threshold the image. So you can take an image of colloidal particles like this one, you threshold it, then you have just white blobs against a background, and then you find the position of each of these blobs by calculating the center of mass of each blob. This is incredibly powerful. With this technique, you can go down to a fraction of a pixel resolution, which is still surprising each time I think about it, because it's a very rough technique. But works incredibly well. And of course, then you can do linking with standard methods such as the Hungarian algorithm and get trajectories that then you can analyze to find out about the structure and the dynamics of your particle system like a colloidal glass. And so this is extremely widely used, this technique. So there are thousands of groups around the world using this technique. The question is, where does it break down? Well, it breaks down when you go to complex systems like this one. So this is a work we were doing some years ago. Maybe the most similar thing to a colloidal glass that you will see in my presentation. Because here you have some particles on the background, those roundish gray shapes, amongst which bacteria move, these shiny fluorescent particles, let's say. These are Bacillus subtilis bacteria. And the point is that, yeah, okay, some video work, other videos don't work, so was expected. So this video will work, and if this video worked, you will see that this is what we tried. We really spent a lot of time. I had a PhD student working for months trying to track this particle with standard methods. What we got was very bad. And if you look at this video, you see why it's very bad. And why it's very bad is because, well, if you look at the all video here, you have a blinking, you have non-uniform illumination, and you have a noisy environment. And you see that we only track a few particles here. So it's very, very bad results. If you could see the video, you will see that more convincingly. But you have to trust me. I know. You can, now you can. There was another video without the tracking below this one. So if you saw that one, then you could notice that it looks like you can track things. But you will notice that, yeah, it's not so easy to decide whether this is a particle or a hole between particles if you look at it carefully. OK. So it was very hard, and that's what made us think, why not to use neural networks? Well, the first neural network we used was this one. And again, I guess all of you know what it is. It's a convolutional neural network with a dense top, which, by the way, breaks translational invariance. That's very important. Before, Victor mentioned that now a very big topic in neural networks is equivariance. Well, this will not work very well with equivariance because it's not translational invariant. So a purely convolutional neural network will probably work better. But anyway, this is a side note. Anyway, so we had this one, and we wanted to input an image of a particle, get at the output the position of the particle. How can we train this? So now we need to train it. To train it, obviously, you need to have data that are at least as good as what you want to get out of it. Obviously, we didn't have data that were as good from our video, because otherwise we will not need a neural network. So what we decided to do, after trying to do it manually, which doesn't work well at all, apart from being incredibly boring, after that, we decided to try with simulated particles, and these are the particles we used. Now, these are not physical simulations of particles. These are just simulation of Bessel functions with some noise and some gradients of illumination. But this was good enough to get a very, very good tracking. So we could train the neural network to track these objects very well. And then what we decided to do was to try to see. Let's see if it runs. Yes. So what we could do is lower than usual, but maybe that's useful. So you can see that in this case, we could track this is an optically trapped particle. So this is a video of an actual particle, physical particle, held in an optical trap. And you can see that the standard algorithm and deep track can track it perfectly, which is nice, but tells us that we can track. And if we compare the trajectory, they fit perfectly. And then we can also compare the distribution, which being an optical trap, we expect it to be a Gaussian. So we expect the probability distribution to be Gaussian. And we see that, in fact, the two distributions coincide and can be fitted perfectly by a Gaussian. And even better, we can even calculate the correlation function of this particle in the trap. And as you can see, the correlation function, it's what we expect, which is an inverted exponential, and fits very well with the theory, the dashed line. Okay? So everything is good and well. We can track things that we could track anyway. So not very useful yet. But then what we did experimentally, this is an experimentally we trapped in our lab, this particle in an optical trap. So what we could do is to switch off the high quality LED illumination and switch on an incandescence lamp next to the setup. As you can understand, that's a very bad way of illuminating your microscopic sample. And what you get is this video. You see that now you have all possible kinds of noise. And OK. And you see that now deep track seems to track the particle very well. But the standard algorithm doesn't really manage to find the particle. Why? Well, because there is noise from, well, it's an incandescence lamp, so you have oscillations, you have background noise, you have gain noise, you have gradients, you have every possible source of noise. And if you look at the trajectory, this is what we get with the standard algorithm, which is obviously wrong. And this one is what we get with deep track, which seems more reasonable. Of course, it's a random process, so we don't really know what we have to get out of it. But we know what are the statistics of the random process. Since this is the very same particle in the very same trap, we expect it to have the same probability distribution, for example. So we expect that the probability distribution should be this one. Well, what we get with the standard method is something that is clearly wrong, but with deep track we get the right one. Even more interesting, we can calculate. We can also reconstruct the yes.
How did you learn the network? Is it the same network as?
Yes,
okay.
It's that network. Okay. The problem with that network is that we train it on simulated data.
Yes.
Works perfectly well, but then we don't really know if it's going to work on real data. So we decided that let's do the analysis. Now, it's a good point. I didn't say that part. We decided let's do it on a real data. What can we do that we can really control? Well, an optically trapped particle. That's why we did this measurement. Yes?
Did you also test with the directional illumination? Because when you have the bacteria around, they are coming in different directions.
Direction illumination? What do you mean?
See here, a change in the illumination, but in a sort of uniform way around the particle.
This one?
Yes.
What
happens if you have,
a gradient, you mean?
A gradient.
Yes, we train for the gradient.
Are you trained?
Yes.
Okay,
so it works well also with gradients. And here, we don't really know what's going on, but we think that there is also a strong gradient. It works very well with gradients. And you can introduce aberrations, whatever you want. I don't do it here, but it works. OK, the other thing we can do is to go and check the correlation function, which is very interesting because the network sees images, which are static objects, doesn't know anything about the fact that these images are in a sequence. But so what do we get with the standard method? We get this autocorrelation function. And if you look at that, anyone who has taken the first course in signal processing knows that that is the correlation function of white noise. It's a peak delta correlation function. It's the Fourier transform of a constant. So it's the Fourier transform of the power spectral density of a white noise. So this practically actually this demonstrates that the information we get from the standard algorithm is pure noise. Not very useful for any purpose, maybe as a noise generator. You can see these small peaks here. I guess you all know what they are. Probably connected with the frequency of the projector. So these are the peaks at 50 Hz. Of course, they are at 100 Hz because these are peaks in intensity. The 50 Hz frequency is the amplitude of the network. What does it tell us in terms of position? Essentially, it tells us that we are in Europe. We cannot be in the US. If not, this will be different. You know, a localization, half of the planet is better than no localization. But anyway, what we get with deep track, it's much better. and we get basically a perfectly reconstructed trajectory. So everything seemed to work. We went back to the original problem, and here you see, actually here is the video, so you see how difficult. It's a zoom in of the video, so that you really see the problems that emerge on this video, and you see that deep track can track it very well. It's good that it works when it should work. So, I mean the video reproduction. And you see that you can even train the neural network to distinguish, identify the bacteria, and separate them from the particle, of course.
So in this case, so before you say you train, you know that you had one particle in
Yeah.
the image. Here, how you go from one particle?
How we did this is in a very inefficient way, because we have this network which is not equivariant, it's not translation invariant. So what we did here, this work, was to basically chop small portion of the video and go over all of them and identify if there is a particle in the center. Now you can ask, how do you ignore the other particles that are around? Well, what we did is to retrain with noise particles around, and the network had to tell us the position of the particle closest to the center. Okay? But this is an extremely inefficient way to do this. What we do now is much better. Simple approach would be a unit, which is fully translation invariant, and I will show later another approach that we developed very recently, which is called Lodestar, but we'll come back in a moment. Any other questions? So it works very well. It works also when we tested against some benchmarks. But now, for the sake of time, let's see what else we can do with machine learning combined with microscopy. And here, one example that can be very interesting is the fact that until now I just showed you the position of a particle. This means that we only know the position. That's why I told you we can just generate circularly looking shapes, and the network will learn to find the center. But in this work, what we wanted to do is to study the physical properties of the particle. So in this case, refractive index and radius. Having an image, which in this case was an holographic image generated by an hologram, an holographic microscope. Well, to do this, then we need to train the network. Again, we want to train on simulated images because it's much more robust. The problem is that in this case, what we had to do is to actually reconstruct a digital twin of the microscope, in a sense, which permitted to simulate the images under the same condition, including all aberrations and so on. And by doing that, we managed to have a very, very good result. We get in this case, of the probability density of the radius estimated by the neural network. And here is the same radius estimated from the diffusion. Since we have a small video of the particle diffusing over a few frames, we can calculate from the diffusion, which would be the standard method. And you see the neural network does incredibly much better. Okay, so we can even, yes?
Just one question. On the left, it seems that the standard method is estimating the radius.
Here is the number of time steps that we use for the estimation. And you see that the standard method, which is the gray one, makes it very wrong. This is the actual value. It's not 1.
But it approaches that value.
Of course, if you have enough time steps, yes. Because the standard method, what it does, essentially, is to take a trace of the particle and to calculate the mean-square displacement and derive the radius from the diffusion constant.
So on the right, we are seeing like the first.
Yes. This is done for the case, I think, if I remember correctly, for 5 time steps. I mean, I will be very fast in the next, just to be clear, I will not go into as much details because I just want to show you a broad range of possibilities, and then, of course, I'm very happy to discuss any of them during the next days. Yeah. Yes. Yes. No, we simulate over a broad range of radii. This is just one plot. We have also a plot where we show that we can distinguish particles that are 100 and 200 nanometers with the same radius, same network. So you generate a large, you can train over a very big range of radii and refractive indices. The interesting thing maybe in this network, since we are going into details, is that here we use a sequence of images and we use some concept that is connected to the concept of attention. Maybe you have heard of transformers and so on. So we basically, without actually knowing, we use essentially attention and not self-attention, to be fair, but we use attention to decide which frames are the most significant for the network to analyze. So that's actually the trick that made the huge difference in the result. Okay, so just to give another example, this is just a very short overview of things done mostly by other groups. And so a lot of work has gone into doing virtual staining. Virtual staining means that you take a tissue. You know, staining when you, for example, when you have blood stains, you want to identify which ones are red blood cells and which one are white blood cells. This requires some chemical staining. This can be substituted by taking standard bright field images and do this with a neural network. This is a nice work done in the group of Ozgan in UCLA. And this is the very famous image from the UNet, which I was mentioning before. As you see, what the UNet managed to do, and this is 2015, so you see that this work was really a pioneering work. They managed to segment cells automatically. This is incredibly difficult. Even nowadays, you have hundreds or thousands of biologists that spend their time manually segmenting cells. And what's the difficulty here? Well, the difficulty is that you need a lot of global information to decide whether any feature of this is a cell, it's a boundary between cells or not. And of course, to do that, the innovation of the of the UNet compared with the standard convolutional autoencoders is that, or encoders in general, is that they introduce this skip connection to retain some information about the geometry of the picture. And another example is this one, again, where they managed to use holographic images to basically segment in different planes cells. As I said, they will be very, very fast. If you have questions, just ask me, something attracts your attention. I didn't really know what would be most interesting for you. This is another example, another topic, a big topic in microscopy combined with deep learning is using deep learning to enhance microscopy, to go beyond what can be done physically. So in this case, for example, you see that you can take a sparse image, nanoscopic image, and then reconstruct the action. I mean, measuring images beyond the diffraction limit is very expensive in terms of time and resources. Here you show that you can take a low-resolution image and transform it into the equivalent high-resolution image, sub-diffraction limited, that you will get with a much more expensive and complex equipment. There is a whole line of research going on that one, on this kind of topics. Another kind of topic is cross-modality transformation. Here, for example, again, these are all work from other groups, just to be clear. So in this work, what they did was to transform an image which was taken with an holographic microscope. Then the advantage of an holographic microscope is that with a single image you have a whole volume. Maybe very interesting for tridimensional glasses. And what they did here is that to take an holographic image and then reconstruct at will any plane of this image as if it had been taken by a bright field microscope. You see how powerful is this technique. The alternative would be to essentially do a Z-scan with a confocal microscope, for example. Another example, again, is this virtual staining. Again, this is done with a UNet. The difference is that to do this now, UNet, typically what you will do is to train them in a different way, which was not mentioned too much in these sessions, which is with generative adversarial approaches, where basically you train two neural networks at once to compete with each other. So that one neural network tries to create a virtual staining and the other neural network tries to tell whether that these are real virtual staining or not. This is the workhorse of all the deep fakes that you find online. Or this is not a real person website. It will use something that is essentially a generative approach. Okay. So this gives you an idea of works done by other groups. Now, some very recent work we have done, which might be particularly relevant for this community. One work, again, I will not go into the details, but I'm very happy to discuss them in detail. In this work, what we have done is to use graph neural networks to reconstruct and analyze the properties of trajectories of particles. So the point is this. Imagine that you have detections in different frames. Then what you can do, like was shown in the talk of Victor, you can connect these frames with graphs and then feed this graph into a graph neural network, and the graph neural network will be able to tell you what are the real trajectories. Much more efficiently and much better than what you can do, for example, with the Hungarian algorithm, especially in edge cases where you have a lot of noise and so on. This is particularly relevant if you have colloidal suspension where things are moving a lot, which I guess is the case for experiments with colloids and glasses before they actually freeze. Because then frame to frame, they move so much that if you use the Hungarian algorithm, you are going to get it wrong. You can use this to do that. This will work. Even better, if you are interested in some global properties or local properties, like local diffusivity of the particles in a glass, well, you can use this algorithm to calculate that without the algorithm having to reconstruct explicitly the trajectories. So you understand that now it's not needed to reconstruct the trajectory to get the properties of the space where the particles live, which is a very powerful thing, especially for cases in which you have a dense collection of particles or particles are very noisy and so on, like blinking particles. This slide doesn't show any of this, just to be clear. It's just that what you can do with this. This slide shows that you can construct, the basic idea here is that you construct a graph and then you feed it to the graph neural network, to these different layers that recursively can reconstruct node properties, edge properties, and global properties. So what are edge properties? Will be, for example, reconstructing the trajectory. What are node properties? Maybe you want to assign to each particle a diffusivity. And what are global properties? Maybe you want to decide whether a glass is frozen or not. And you can get the network to learn to do that. One interesting possibility that arises with this is also try to use graph neural network within other systems, in particular within autoencoders, as mainly even better with variational autoencoder, because then you could probably get out the structure of things without having to actually plug in the number of phases or possibilities that you have in advance. So that would be a very nice possibility. So, second thing, okay, imagine that there is nothing. Until now, every neural network I spoke about required a lot of training, right? So, neural network means that you need a lot of data. Ideally, you need labeled data, which means that you need to have a ground truth. And lots of data for tracking, for example, might mean hundreds of thousands of particles that have been tracked or simulated. But you need to have this huge amount of data and this ground truth. What we developed here was a new technique to track particles where we need only one single crop. So just crop one particle, that's it. And you don't even need to know the ground truth. With that, you will be able to track the particle. And just to give you an idea, these are simulated data. So you see that it works. It works here to track this point particle. That's a very easy case. But the nice thing is that we train with a single crop. It works over all these noise levels. You see that, so it's not obvious. You see that the noise level changes randomly, essentially, and it still be able to track it. But it works also for other particles, other shapes of particles. So all of these are simulated particles where, with a single crop, without telling the network where is the particle, well, it learns how to track it. Now, you might ask, how does it work? How can it learn with only one particle, one crop, without knowing the ground truth? Well, because it exploits inherent symmetries in the problem. So it's an equivariant approach. So in this case, what we do essentially is to say, just to give you an intuition for this method, well, if I have a crop of a particle, I don't know where is the particle. I just know that there is a particle. What I know, though, is that if I shift or I translate my crop by a certain amount, also the position of the particle will translate by the same amount. I don't know where the particle is, but as long as I translate my crop, also the particle position must translate by the same amount. Now you see how this is not enough to have an error signal that you can use for training the network, but if you do this in two different directions, well, then you have a differential error signal that you can use for training the network. It's a slightly more complex. You need to use a bit more symmetries, not only translation, but also rotation. But once you do that, you see that it works incredibly well. And when I say incredibly well, it's because in these cases, we managed also to demonstrate that this is basically at the limit of detection. So there is the Kramer-Rao limit, which is essentially tells you what is the limit for detection, for accuracy in detection for a particle when you have some noise. And this touches the Kramer-Rao limit. You literally cannot do better than that. Now, what can you do? Of course, this works on these simulated images. Nice. Can we do on real experiments? Yes. So these are experimental data. Let's see if it runs. Yes. So you see that in this case, we have cells that are growing over time. These are all from the cell tracking challenge. And you see that this is the map, the heat map that the network generates to then track the particles. Keep in mind that this is trained on a single cell, on a single crop of a cell. And same for this one, where it becomes even more interesting because here the cells change shape. So it's really surprising the power of generalization that we can achieve by just using symmetry principles. Here, look at the diversity of the cells. And finally, the last two ones are nice because here you see that here we track these objects or their mouth, let's say. And this depends on how big we make the crop. So depending on the size of the crop, we'll be able also to tune more or less what kind of object we are going to, the network is going to focus on within in its tracking. Okay, this is very interesting, and I think it's especially interesting because this is not only for tracking. This method can be applied to any problem to which you have in which you have symmetries that produce an equivariance, which you can exploit. So we do this here for position, but in the paper we do it also for Z position using equivariance in holography. We do it for polarizability estimation, again using equivariance in Z direction. And I can imagine that the same kind of approach can be used, maybe combined with a graph neural network, to study your glassy system, as long as you find some properties that are equivariant. Energy, whatever you can think of, can be exploited probably with exactly the same principles. And then you have the power that you can get results with only a single image or single data point and without knowing the ground truth. Okay, and these are maybe less related with the glasses, even less related with glasses, but still interesting. So, well, all of you are aware of climate change and the importance of carbon, and all of you probably don't think too much about the fact that most of the carbon is actually managed by marine ecosystems and by plankton. So they absorb most of the carbon. And most of you probably don't know that no one has ever seen plankton moving around and eating and so on, being able to actually track a single plankton over the whole life cycle from when it's born until it dies, see how much they eat, which kind of species they like and don't like. So this is information that was missing. So we developed a technique in which we combine essentially a holographic microscope with deep learning and permits us then to follow plankton. Here we see, for example, an example of one plankton, a predator plankton eating a prey. So we can now really quantify these kind of things. We can also show over the full life cycle of the plankton. By the way, we can also measure the mass in real time of the plankton. So we know how much it weighs, we know how much of the prey it eats. We don't just know that it's eating it, we know also that it's consuming it completely. We can do the same with cell division. We can follow the plankton all over their cells life cycle. So far we developed the technique, but now our collaborator at the Marine Science Department in Gothenburg University are actually doing some new science using this technique, not just developing the technique itself. And as another example, here it's just a combination of holography with, of machine learning with some new techniques for measuring molecules. So one of the problems with molecules is that you would like to measure the smaller molecules possible. And with this, essentially what we do here is to send a molecule inside a nanochannel. And you see that then there is the dark spot. And again, by using some complex machine learning approach, we can see that we can follow the particle, the molecule perfectly. These are 50, down to 50 kilodalton molecule, which are very small. Now, maybe you don't, probably you know what are daltons. I didn't know when I started because I don't really use daltons usually, but then I figured out that one dalton means one nucleon. So, you know, then you get an idea what a dalton is. So we can follow the molecules, but we can also characterize again their size and their diffusivity. And from that, we can get a lot of information about how elongated they are and so on. So you can actually study molecules down to a limit of detection that was not reached before. Now we already, it's not published that yet, but we went down even lower than 50 kilodalton now. So now I will claim this technique is actually more, it's probably the most label-free way of tracking molecules is probably the most, the one that reaches the lowest molecular size. Okay, so this gives you an overview of examples of things you can do by combining machine learning with microscopy. How much time do I have? I don't know.
I think you're done.
Okay. That's what I suspected. So as I said, I will not really discuss this too much because the only point of this is very quick, is that this is based on a software which is DeepTrack. Now it's in version 2.1, but you can still access it. Well, the name now is the repository is DeepTrack 2. But if you access this one, you will still find it. It's a fully documented software, very well programmed in the sense it's really by the standards of software engineering. And it's a full package that permits to actually you do essentially any kind of machine learning applied to microscopy, including the important part of simulating the data where needed, and feeding these simulations into a pipeline that permits to train with a generator, a neural network, generating in real time data as needed, using GPU and so on. So this is a fully developed and still ongoing project where we keep on developing. And if any of you is interested in using it in any application or interested in contributing, just let me know. And it's fully documented. We have a lot of tutorials. And this is just to show you more or less the idea behind it, the original idea, but doesn't really matter too much. All of these are examples of tutorials that were provided with the original paper of DeepTrack. So we classify the NIST, we do what I showed here. I'm not going to show you any of this because it's essentially the same things I showed you. I just want to show you the last one because the last one is actually the last two ones. So this one is a nice example where the problem is to count the cells. This was a challenge, in the sense a challenge on Kaggle, I think, in which you have to count the cells. And what we did was essentially, in this case, we developed a system where we can count the cells by transforming each cell into a Gaussian blob that has intensity 1, and then we just sum up the pixels. And this is done by simulating the cells for the training. So these are simulations done with DeepTrack of the cells. You see how well they are simulated. And then when applied to the real data, it works extremely well. So you see that we have a very, very high correlation between the predicted count and the true count. Predicted count, since this was a challenge, some biologists actually counted the cells one by one. That's the predicted count. And of course, you can argue, yes, but you could just take the total intensity of the original image, and then what you get? Well, if you do that, you get this, this gray result on the background, which is still correlated with the number of cells, but not so well as what the neural network can do. So it's actually an improvement over that. Another example that might be interesting is this one, where the idea is to go from a segmented version of a tissue to a tissue that looks like the correct one. And this is done with a GAN, one of these generative adversarial network approaches. Here, what we do essentially is to have a UNet as the generator and a standard discriminator, which is essentially a converging convolutional neural network, which tells us whether it's real or not. The challenge with any generative adversarial approach is that you need to train two neural networks at the same time against each other, which practically means you need to ensure that the losses of both of them decrease at the same rate. If they don't decrease together, if the generator becomes too good or the discriminator becomes too good, there is no real signal anymore in the network to train further. So the real trick here is to balance the losses between the two networks, and it works very well. So the outcome is this one, and you see that the generated image is as plausible as the real image. And with that, I will conclude. Very last slide. If you are interested, we are now, well, we are asked to give a course in ETH, which is running this semester. These are the first two modules. There will be a third module. This course covers essentially everything in machine learning applied to microscopy, starting from the single neuron, single regression but going up to, it's not shown here, but in the last module we will go up to graph neural networks, generative adversarial model, even diffusion models, which are all the rage right now. If you're interested, let me know. It's not publicly available right now, but it will be made publicly available in some form very soon. We have written all the documentation so that it can be for self-study. There are like 1,000 pages of examples, worked out examples. If you're interested, let me know. And with that, I would like to thank you.
Thank you. Questions?
Oh, I exceeded my time.
Thank you. It was really impressive. Like I was wondering, in the case where you train only on one cropped image,
yes.
right? Like you had this example where it was actually tracking many different cells that looked very different, right?
Mm-hmm.
It was great because in this case all of them were cells, right? I was wondering, like compared to the first case where you showed that you train on very, rounded particles and you could discriminate between them and other particles that were not rounded. In this case, I guess there is a trade-off, right? Between if you want to discriminate very well between different types of particles or not. Like how do you do this?
Your question is whether how much is the discriminative power, I guess.
Yeah, in this case, I guess it will track anything.
It will
right?
track better the particles you have trained for. It will track also other things. And this is shown in the first figure of the paper because it was also my first question when, when we discussed this technique. So just to give you an idea, if I train for the round shape at the beginning, so if I train for that one, so if I train for this one, it will track this better than the others. If I train for this one, it will track that better than the other. So, but it will still track the others because at the end it's learning the principles, the symmetry principles. But if you train to track this, it will not really track something like this that doesn't have the mouse of this plankton.
Okay. So you could have something like a threshold and discriminate.
Yeah,
okay.
Yes, you can always do that.
Okay.
And the reason why you train only on one and then you can apply to all is because it's based on this principle, and then essentially what we use is a convolutional neural network, a telescopic convolutional neural network that is translation invariant by itself, and then has a finite receptive field. So this neural network will really not see what else is too far away. That's why it doesn't get confused.
Very nice. Thank you.
Other questions?
I think it's
so. Yeah, maybe I have a comment. So there will be, I think, a nice application. It's a pity that the person related to this couldn't be here today. So there are experiments done on colloids, which are actually done by Paddy Royal.
Mm-hmm.
So the idea was to go to very small colloids in such a way that you can study glassy physics experimentally on larger time scale because they are smaller. So I mean, the experimental time scale is always the same. Then the problem is really that then becomes the tracking, because then when you go to very, very small sites, then it's very difficult to track. And I know that it's a particular problem for him, and he's looking possible solution. So
I think this will be the perfect solution,
yeah,
because then you don't need the tracking.
Yeah.
You can really bypass the tracking, especially if you go to very small colloids that diffuse so much that when they're close together, you don't really know which one was which. Okay. That's a very big problem in the field, but this completely solves it because it doesn't need that information. Unless you want to reconstruct the trajectory, you don't really need to reconstruct the trajectory in order to get information that you want about your system.
Well, okay.
So it's actually I think it's the most interesting thing of applying graph neural network to this kind of problems, that you can bypass that need.
Okay, so I think this is certainly, I think, a topic
it would be
that
great to speak with him, since now he's in
Paris.
Paris.
In tracking. Yeah.
So most of your movies were in 2D. Does it generalize as well to 3D data too? Or?
Yes, there were some movies in 3D with, well, no, real 3D there was not. There was holographic data, which are 3D, but they are still 2D movies. But you can, if you have fast acquisition in 3D and you have a volume, you can literally put the volume as input instead of and it's really no problem. Of course, the computational complexity increases in terms of training, but we have done in other works cross-modality transformation between, I mean, that's for brain imaging, so completely different field. I've not spoken about it at all, but what we have done is to transform scans made with CT scans into MRI scans, which are more expensive, more difficult to come by, and that works, and that's 3D to 3D volumes.
Other questions? All right, if not, thank you again.
Thank you.
And, so we reconvene here at 2 p.m. for the afternoon session.